Welcome to the lesson on Euclid's division lemma. At the end of this lesson, you will be able to state the principle of Euclid's division lemma and calculate the highest common factor of any two positive integers by applying Euclid's division lemma. You will also be able to identify certain properties of numbers by applying Euclid's division lemma. Meet Mr. Chatura. He runs a stationery shop. To keep a track of all the items in his shop, he uses a special form. Right now, he's checking his stock. Let's take a closer look at his form. The first column of this table shows the names of different items Mr. Chatura sells. The second column shows the number of items in standard boxes available. Now, let's follow Mr. Chatura as he fills his table. Each box of pencils has 12 pencils, and Mr. Chatura has 5 such boxes. This means that there are 60 pencils in the boxes. He also has 3 extra pencils. Thus, the total number of pencils is 63. Each box of erasers has 10 erasers, and Mr. Chatura has 8 such boxes. This means that there are 80 erasers in the boxes. He also has 6 extra erasers. Thus, the total number of erasers he has is 86. Each box of sharpeners has 8 sharpeners, and Mr. Chatura has 4 such boxes. This means that there are 32 sharpeners in the boxes. He does not have any additional sharpeners. Thus, the total number of sharpeners is 32. Each box of ballpoint pens has 15 pens. But right now, Mr. Chatura doesn't have a complete box. He has 10 extra ballpoint pens. Thus, the total number of ballpoint pens he has is 10. Now pay attention to the values in each row of the table. In the first row, the total 63 is equal to 12 multiplied by 5 plus 3. Similarly, in the second row, 86 is equal to 10 multiplied by 8 plus 6. The last two rows are interesting. In the third row, we can say 32 is equal to 8 multiplied by 4 plus 0. Similarly, in the fourth row, 10 is equal to 15 multiplied by 0 plus 10. Now, let us come to the point. If we assign labels to the values in the different columns of the table, we can see that they all follow a general relation. The total A is equal to the pieces per box, B, multiplied by the number of boxes, Q, plus additional items, R. This relation is known as Euclid's division lemma, which states that for any two positive integers, A and B, we can find two whole numbers, Q and R, such that A is equal to B multiplied by Q plus R. From Mr. Chatura's table, you can see that Euclid's division lemma holds true even if either Q or R is 0. Now suppose Mr. Chatura discovers he has 12 extra pencils instead of 3. What happens to Euclid's division lemma in this case? 12 pencils add up to one complete box. So we see that if R becomes equal to B, the value of Q increases by 1 and the value of R is reduced to 0. Thus, the value of R in the equation for Euclid's division lemma can be greater than or equal to 0 and less than the value of B. Mr. Chatura has got a fresh stock of pencils and erasers. He is making space to arrange them on the shelves. Mr. Chatura has got 520 boxes of pencils and 140 boxes of erasers. He wants to arrange them in the least number of shelves, such that each shelf has an equal number of boxes of pencils and an equal number of boxes of erasers. Mr. Chatura has figured out a solution. All he has to do is find the highest common factor, or HCF, of 520 and 140. Now, how does he do that? Mr. Chatura can use Euclid's division lemma to find the HCF of 520 and 140. Let's see how. Let's apply Euclid's division lemma to the two numbers taking the larger number equal to A and the smaller number equal to B. Dividing 520 by 140, we see that 140 goes into 520 3 times and leaves a remainder of 100. Now consider the value of B and R in this equation. We see that R is not 0. So let's apply Euclid's division lemma, taking 140 as A and 100 as B. Dividing 140 by 100, we see that 100 goes into 140 once and leaves a remainder of 40. Now consider the values of b and r in this equation. We see that r is not 0. So let's apply Euclid's division lemma, taking 100 as a and 40 as b. Dividing 100 by 40, we see that 40 goes into 100 two times and leaves a remainder of 20. Now consider the values of b and r in this equation. We see that r is still not 0. So let's apply Euclid's division lemma, taking 40 as a and 20 as b. Dividing 40 by 20, we see that the 20 goes into 42 times and leaves a remainder of 0. Note that in this equation, the value of r has become 0. The value of b in this case, that is 20, which is the HCF of the numbers 520 and 140. By Euclid's division lemma, we found that HCF of 520 and 140 is 20. Thus, Mr. Chatura can arrange his stock in 20 shelves, each having 26 boxes of pencils and 7 boxes of erasers. Now, let's observe the process of finding the HCF of any two given positive integers using Euclid's division lemma. Suppose we have two positive integers, a and b, such that a is greater than b. Apply Euclid's division lemma to the given integers a and b to find two whole numbers q and r, such that a is equal to b multiplied by q plus r. Check the value of r if r is equal to 0. Then, b is the HCF of the given numbers. If r is not equal to 0, apply Euclid's division lemma to the new divisor b and the remainder r. Continue this process till the remainder r becomes 0. The value of the divisor b in that case is the HCF of the two given numbers. Euclid's division algorithm can also be used to find some common properties of numbers. Let's take this problem to show that every positive odd integer is of the form 2q plus 1. Let a be any positive odd integer. Then, by Euclid's division lemma, we can write a is equal to b multiplied by q plus r. If we take the value of b as 2, we can write a is equal to 2 multiplied by q plus r. By Euclid's division lemma, the value of r can be greater than or equal to 0 and less than b. Since b is equal to 2, the possible values of r are 0 and 1. Putting in the values of r as either 0 or 1, we get the possible values of a as either 2q or 2q plus 1. Now the value of a cannot be 2q, since 2q is divisible by 2 and a is an odd integer. Thus we can say that any positive odd integer can be of the form 2q plus 1. You've reached the end of this section. Let's have a quick recap of the key points covered in this section. Recall that Euclid's division lemma states that for any two positive integers a and b, we can find two whole numbers q and r, such that a is equal to bq plus r, where r is greater than or equal to 0 and less than b. Euclid's division lemma can be used to find the highest common factor of any two positive integers. It can also be used to show the common properties of numbers. You can now proceed to the next section. Hope you enjoyed this learning experience. Welcome to the lesson on the fundamental theorem of arithmetic. At the end of this lesson, you will be able to state the fundamental theorem of arithmetic. You will also be able to apply the fundamental theorem of arithmetic to calculate the prime factors, the HCF, and the LCM of any two composite numbers. Meet Mr. Number Maker. He's an old vagabond who's always on the move, but he has a special skill. Mr. Number Maker claims that he can produce any composite number you can think of. He uses a special set of tools to do so. Let us take a look at these tools. Oh, so Mr. Number Maker's tools are just a set of numbers. But these numbers are special. Observe carefully. What kind of numbers are these? All these are prime numbers. In fact, Mr. Number Maker has an infinite collection of all the prime numbers in his magical suitcase. Let's verify Mr. Number Maker's claim. Let's take a number. Any number. Say 1950, the year India adopted its constitution. Now, let's create a factor tree for this number using Mr. Number Maker's tools. Dividing 1950 by 2, we get 975. Dividing 975 by 5, we get 195. Dividing 195 by 5 again, we get 39. Dividing 39 by 3, we get 13. Now, 13 itself is a prime number, so we cannot factorize it any further. Thus, we see that 1950 can be expressed as a product of 2, 5, 5, 3, and 13, each being a prime number. What is true for 1950 is true for any composite number you can think of. Mr. Number Maker's claim is based on the fundamental theorem of arithmetic that states every composite number can be expressed or factorized as a product of prime numbers. Is there any other way to factorize 1950 using prime numbers? Let us see. Starting with 5 instead of 2, we get another set of prime factors for 1950. How are these factors different from the earlier ones? Note that the set of prime factors for 1950 still remains the same. Only the order of the prime factors has changed. This brings us to the complete statement of the fundamental theorem of arithmetic that states that every composite number can be expressed or factorized as a product of prime numbers, and this factorization is unique except in the order of prime factors. We can write the prime factorization of a number in the form of powers of its prime factors. Let us see how this is done. This is how it is done. Since 5 occurs twice in the prime factorization of 1050, its power is 2. Since 2, 3 and 13 occur once in the prime factorization of 1950, their power is 1. Mr. Number Maker has another interesting tip for you. He says that by expressing any two numbers as the product of their prime factors, you can easily calculate their highest common factor, that is, the HCF, and the lowest common multiple, that is, the LCM. Now, let us see how this is done. Let's put Mr. Number Maker's tip to use. We already have the prime factorization of 1950. Now, let's take another number, say 2010, the year India hosts the Commonwealth Games. Let's find the prime factorization of 2010. Dividing 2010 by 2, we get 1005. Dividing 1005 by 5, we get 201. Dividing 201 by 3, we get 67, which itself is a prime number. Thus, we see that 2010 can be expressed as a product of 2, 5, 3, and 67, each being a prime number. Since all the prime factors of 2010 appear once in its prime factorization, the power of each of them is 1. Now, let us consider the prime factorization of 1950 and 2010 together. Let us first find the highest common factor, or HCF, of these two numbers. To find the HCF of the two given numbers, locate the common factors in their prime factorization. 2, 3, and 5 are the common factors in the prime factorization of 1950 and 2010. Next, find the product of the terms containing the least powers of common prime factors of the two numbers. Let's see what this means. Since the powers of common factors 2 and 3 are 1 in both the cases, their power will remain 1 while calculating the HCF. The powers of common factor 5 in the prime factorization of 1950 and 2010 are 2 and 1 respectively. We will use the power 1 in calculating the HCF since it's the smallest power of 5. Thus, the HCF of the given numbers is 2 into 3 into 5 or 30. Now, let us first find the least common multiple, or LCM, of these two numbers. The LCM of two numbers is given by the product of the terms containing the greatest power of all prime factors of the two numbers. Since the greatest power of the common factors 2 and 3 are 1 in both the cases, their power will remain 1 while calculating the LCM. The power of common factor 5 in the prime factorization of 1950 and 2010 is 2 and 1 respectively. We will use the power of 2 in calculating the LCM since 2 is the greatest power of 5. The remaining prime factors 13 and 67 is the prime factorization of the two numbers who appear in the power of 1 in the LCM. Thus, the LCM of the given numbers is 2 into 3 into 5 square into 13 into 67, or 1,30,650. By now, we have expressed two randomly selected numbers as products of prime numbers. We have also used their prime factorization to calculate their HCF and LCM. Now, let us look at another interesting relation. Let us find the product of 1950 and 2010. First, let us find the product of the HCF and LCM of the given numbers. What do you observe? Note that the product of the given numbers is equal to the product of their HCF and LCM. This result is true for all positive integers and is often used to find the HCF of two given numbers if their LCM is given and vice versa. You've reached the end of this section. In this section, you learnt about the fundamental theorem of arithmetic. The theorem states that every composite number can be expressed or factorized as a product of prime numbers, and this factorization is unique except in the order of prime factors. You have also learned that the HCF of two numbers is equal to the product of the terms containing the least powers of the common prime factors of the two numbers. The LCM of the two numbers is equal to the product of the terms containing the greatest powers of all prime factors of the two numbers. And the product of two positive integers is equal to the product of their HCF and LCM. Welcome to the lesson on revisiting rational and irrational numbers. At the end of this lesson, you will be able to distinguish between rational and irrational numbers. You will also be able to prove theorems related to rational and irrational numbers. There is a big commotion at the Rational Numbers Club. The club is exclusively for rational numbers, but it appears some trespassers have gotten inside. It seems the rational numbers have identified the trespassers as irrational numbers, but the trespassers insist they too are rational numbers. This debate is really getting heated. Well, the law of Numberland has taken its course, and the accused trespassers have been summoned in court. The accused still insist they are rational numbers. Here is Mr. Public Prosecutor, who believes that the accused are irrational and not rational numbers. Let us see how he presents his case. Mr. Public Prosecutor is kind enough to present his notes on this screen for all of us to see. Mr. Public Prosecutor is starting by introducing the two parties to the case. A number is called rational if it can be written in the form P upon Q, where P and Q are integers and Q is not equal to 0. A number is called irrational if it cannot be written in the form of P upon Q, where P and Q are integers and Q is not equal to 0. The accused still stand by their claim of being rational numbers, but Mr. Public Prosecutor is all set to begin his argument. Let us hear what he has to say. The theorem Mr. Public Prosecutor wants to present states that if a prime number P divides Q square, then P also divides Q, where Q is a positive integer. To prove the theorem, let us assume that Q is a positive integer whose prime factors are P1, P2, P3 to Pn, not necessarily distinct. Thus, Q square is equal to the product of the squares of P1, P2, P3 to Pn. It is given that the prime number P divides Q square. By the fundamental theorem of arithmetic, Q square has a set of unique prime factors P1, P2, P3 to Pn. Thus, P is one of the prime factors of P1, P2, P3 to Pn. But P is also a factor of Q. Thus, we can say that if a prime number P divides Q square, then P also divides Q, where Q is a positive integer. Where is this argument heading? Is Mr. Public Prosecutor accepting that square root of 2 is a rational number? If we assume square root of 2 is a rational number, then by definition, two integers must exist, P and Q, where Q is not equal to 0, such that square root of 2 is equal to P upon Q. Now, suppose P and Q have a common factor, R, other than 1. Dividing both P and Q by R, we get root 2 equal to A by B, such that A and B are two co-prime integers. This means that A and B have no common factors other than 1. In this condition, a rational number is said to be in its standard form. So, we have square root of 2 equal to A by B. Squaring both the sides and rearranging the equation, we get 2 times B square is equal to A square. This means 2 divides A square. Since 2 divides A square by the earlier theorem, we proved that 2 divides A. Thus, we can also say that A is equal to 2 times C for an integer C. Putting the value A is equal to 2 times C in the previous equation for A and B, we get 2 times C square is equal to B square. This means 2 divides B square. Since 2 divides B square by the earlier theorem, we proved that 2 divides B. Now, wait a minute, there's a contradiction here. Since 2 divides both A and B, it is a common factor of A and B. This contradicts the fact that A and B are co-prime numbers and have no common factors other than 1. This contradiction has arisen because of our first assumption that square root of 2 is a rational number. Hence, saying square root of 2 is a rational number is incorrect. Thus, Mr. Public Prosecutor has proven that square root of 2 is an irrational number. Let us see if square root of 3 can satisfy the condition of being a rational number. If we assume square root of 3 is a rational number, then by definition, two integers must exist, p and q, where q is not equal to 0, such that the square root of 3 is equal to p upon q. As before, suppose p and q have a common factor r other than 1. Dividing both p and q by r, we get square root of 3 equal to a by b, such that a and b are two co-prime integers. This means that a and b have no common factor other than 1. So, we have square root of 3 is equal to a by b. Squaring both sides and rearranging the equation, we get 3 times b square is equal to a square. This means 3 divides a square. Since 3 divides a square by the earlier theorem we proved, we can say that 3 divides a. Thus, we can also say that a is equal to 3c for some integer c. Putting the value a is equal to 3c in the previous equation for a and b, we get 3 times c square is equal to b square. This means 3 divides b square. Since 3 divides b square by the earlier theorem we proved that 3 divides b, so we arrive at the same contradiction. Since 3 divides both a and b, it is a common factor of a and b. This contradicts the fact that a and b are co-prime and have no common factor other than 1. This contradiction has arisen because of our first assumption that square root of 3 is a rational number. So, saying square root of 3 is a rational number is incorrect. Mr. Public Prosecutor has thus proven that square root of 3 is also an irrational number. Now, let us see if 2 plus square root of 3, which is the sum of a rational and irrational number, is a rational or irrational number. If we assume 2 plus square root of 3 is a rational number, then by definition, there must exist two co-prime integers, a and b, where b is not equal to 0, such that 2 plus square root of 3 is equal to a by b. Rearranging the equation, we get square root of 3 is equal to a minus 2b upon b. This is a rational number, since a and b are both integers. We again face a contradiction here. The equation here shows that square root of 3 is equal to a rational number. This contradicts that square root of 3 is an irrational number. We have already proven this. This contradiction has arisen because of our first assumption that 2 plus square root of 3 is a rational number is incorrect. Mr. Public Prosecutor has thus proven that 2 plus square root of 3 is also an irrational number. The judge's verdict has arrived. It says that a number that cannot be written in the form a upon b, where a and b are integers and b is not equal to 0, are called irrational numbers. The verdict further says that the sum, the difference, the product, or the quotient of a rational and an irrational number is also an irrational number. The irrational numbers have accepted they are different, but they now allege that all the rational numbers are also not the same. What are they hinting at? The judge has asked the public prosecutor to intervene. Let us hear what he has to say. On this issue, Mr. Public Prosecutor seems to agree with the irrational numbers. According to him, the rational numbers are of two different kinds. Let us look at a few examples of rational numbers to see how they are different. The decimal form of the rational number 3 by 8 terminates or has a finite number of digits. The decimal form of the rational number 5 by 3 does not terminate. It has an infinite number of digits and is a recurring decimal number. The decimal form of the rational number 16 by 25 terminates or has a finite number of digits. The decimal form of the rational number 7 by 11 does not terminate. It has an infinite number of digits and is a recurring decimal number. Thus we see that rational numbers are of two types depending on whether their decimal form is terminating or recurring. If a rational number is not expressed in its decimal form, is there any way to tell whether its decimal expansion terminates or not? Let us see what is so special about the rational numbers whose decimal expansion terminates. Do you notice a pattern when we express these rational numbers in a decimal form? Note that for all these rational numbers whose decimal expansions terminate, the prime factorization of the denominator has the power of 2 or 5 or both. Mr. Public Prosecutor has introduced a theorem that says that if P upon Q is a rational number such that the prime factorization of Q is of the form 2 raised to the power of A into 5 raised to the power of B, where A and B are positive integers, then the decimal expansion of the rational number P upon Q terminates. Does this theorem in any way apply to rational numbers written as terminating decimals? Here are some rational numbers which are terminating decimals. Let us see what Mr. Public Prosecutor intends to do with them. Let us write all these terminating decimals as rational numbers of the form P upon Q. Note that for all these rational numbers, the prime factorization of the denominator has power of only 2 or 5 or both. Mr. Public Prosecutor has introduced another theorem that says that if a rational number is a terminating decimal, it can be written in the form P upon Q, where P and Q are co-prime, and the prime factorization of Q is of the form 2 raised to the power of A into 5 raised to the power of B, where A and B are positive integers. So, how can you identify a rational number whose decimal expansion does not terminate or is recurring? Mr. Public Prosecutor seems to have a theorem for this also. Mr. Public Prosecutor has introduced another theorem that says that if P upon Q is a rational number such that the prime factorization of Q is not of the form 2 raised to the power of A into 5 raised to the power of B, where A and B are positive integers, then the decimal expansion of the rational number P upon Q does not terminate and is recurring. The trespassers in the Rational Numbers Club have accepted that they are irrational numbers and different from rational numbers. The rational numbers too have accepted that they are of two different kinds, that is, terminating and recurring decimal types. This seems to be heading for a happy ending. The rational and irrational numbers have decided to forget their differences and become friends. Don't you think we too can take a cue from them and live happily together? You reached the end of this section. Let's have a quick recap of the key points covered in this section. A number is called a rational number if it can be written in the form of A by B, where A and B are integers and B is not equal to 0. A number is called an irrational number if it cannot be written in the form of A by B, where A and B are integers and B is not equal to 0. The sum, difference, product, or quotient of a rational and an irrational number is also an irrational number. Rational numbers are of two types depending on whether their decimal form is terminating or recurring. If a rational number is a terminating decimal, it can be written in the form P upon Q, where P and Q are co-prime and the prime factorization of q is of the form 2 raised to the power of a into 5 raised to the power of b, where a and b are positive integers. If p upon q is a rational number such that the prime factorization of q is of the form 2 raised to the power of a into 5 raised to the power of b, where a and b are positive integers, then the decimal expansion of the rational number p upon q terminates. If p upon q is a rational number such that the prime factorization of q is not of the form 2 raised to the power of a into 5 raised to the power of b, where a and b are positive integers, then the decimal expansion of the rational number p upon q does not terminate and is recurring. You can now proceed to the next section. Hope you enjoyed this learning experience. Welcome to the lesson on the geometrical meaning of the zeros of a polynomial. At the end of this lesson, you will be able to define a polynomial and its basic terminology. You will also be able to identify the zeros of a polynomial by plotting it on a graph. Consider the expression 5x cubed minus 2x squared minus x plus 2. This expression is called a polynomial. A polynomial is an algebraic expression consisting of multiple terms. The terms of a polynomial can be variables or variables raised to a power of a whole number, a constant, or the product of these two. The real number that precedes the variable is called the coefficient. For example, in this polynomial, 5, 2, and 1 are the coefficients. In this polynomial, there is only one variable, x. Such a polynomial is called a polynomial in one variable. If x is the variable in a polynomial, then the polynomial is denoted by f of x, p of x, q of x, and so on. The highest part of the variable of a polynomial is called the degree of the polynomial. Based on its degree, a polynomial can be called as linear polynomial, quadratic polynomial, cubic polynomial, and so on. Since the highest degree of this polynomial is 3, this is a cubic polynomial. The general form of a cubic polynomial is ax cubed plus bx squared plus cx plus d, where a, b, c, and d are real numbers, and a is not equal to 0. Here's a second example. As the highest degree of this polynomial is 1, it is a linear polynomial. This is read as p of x is equal to 4x plus 8. The general form of a linear polynomial is ax plus b, where a and b are real numbers and a is not equal to 0. Consider the third polynomial, x squared minus 4x plus 3. Here the highest degree is 2. Such a polynomial is called a quadratic polynomial. The general form of a quadratic polynomial is ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. Now that we have reviewed the definition of a polynomial, let's move on to define the zero of a polynomial. Consider the quadratic polynomial x squared minus 4x plus 3. Let's substitute the value of x as 1 in the polynomial and simplify it. We get the value of the polynomial as 0. This implies that p of 1 is equal to 0. Here the value 0 is the value of the polynomial when the value of x is equal to 1. Now, let's substitute the value of x as minus 1. On simplifying, we get the value of the polynomial as 8. This implies that p of minus 1 is equal to 8. Here the value 8 is called the value of the polynomial when x is equal to minus 1. In general, the value of a polynomial p of x when x is equal to k is the value obtained by substituting x as k. Here k is a real number and the value of the polynomial is denoted by p of k. Now in the first case, the value of the polynomial is 0 when the value of x is 1, which is the value of x, and it is called the 0 of the polynomial. The 0 of the polynomial is defined as any real value of x, for which the value of the polynomial becomes 0. In general, a real number k is a 0 of a polynomial p of x if p of k is equal to 0. Let's discuss the geometrical meaning of the zeros of a polynomial. Here, we will see the graphical representation of a polynomial. Consider the linear polynomial 4x plus 8. Assume that the polynomial is equal to y. To determine the geometrical meaning of the zeros of this polynomial, we'll have to plot this equation on the graph. You must first determine the points representing the x and the y coordinates. For this, we'll assume a few values for x. Substituting these values of x in the equation and simplifying it will give us the values of y. This table gives the x coordinates and the corresponding y coordinates. The x coordinate and the corresponding y coordinate together form an ordered pair that represents a point. Let's locate these points on the graph. On joining all these points, we get a straight line. As you can see, this line intersects the x-axis at the point -2, 0. This means that the line intersects the x-axis when x is equal to -2. As per the definition of the 0 of a polynomial, the 0 of this linear polynomial is -8 upon 4. This implies that the 0 of this polynomial is -2. Based on these observations, we can conclude that the x-coordinate of the point where the graph intersects the x-axis is the 0 of the polynomial. In general, if a polynomial p of x intersects the x-axis at k, 0, then we can say that k is the 0 of the polynomial. In other words, p of k is equal to 0. The graph of a linear polynomial intersects the x-axis at a maximum of 1 point. Therefore, a linear polynomial has a maximum of 1, 0. Similarly, we can plot the graphs for quadratic and cubic polynomials. We can also find the zeros of these polynomials by identifying the points where the graphs of the polynomials intersect the x-axis. Let's summarize the observations from the graphs. The graph of a quadratic polynomial intersects the x-axis at a maximum of 2 points. Therefore, a quadratic polynomial can have a maximum of 2 zeros, 1, 2, or no zeros. In case of a quadratic polynomial, the shape of the graph is a parabola. The shape of the parabola of a quadratic polynomial depends on the coefficient of x square. If a is greater than 0, then the parabola opens upwards. If a is less than 0, then the parabola opens downwards. The graph of a cubic polynomial intersects the x-axis at a maximum of 3 points. Therefore, it has maximum of 3 zeros. That is, it can have 1, 2, 3, or no zeros. In general, an nth degree polynomial intersects the x-axis at a maximum of n points. Therefore, an nth degree polynomial has a maximum of n zeros. You have reached the end of this section. Before moving on to the next section, let's recap the key points. The x-coordinate of the point where the graph of a polynomial intersects the x-axis is called the zero of the polynomial. An nth degree polynomial intersects the x-axis at a maximum of n points, and therefore has a maximum of n zeros. The graph of a quadratic polynomial is a parabola. The shape of a parabola of a quadratic polynomial depends on the coefficient of x square. If a is greater than 0, then the graph is a parabola that opens upwards. If a is less than 0, then the graph is a parabola that opens downwards. Hope you enjoyed this learning experience. Welcome to the lesson on the relationship between zeros and coefficients of a polynomial. At the end of this lesson, you will be able to establish the relationship between the zeros and the coefficients of linear polynomials, quadratic polynomials, and cubic polynomials. Let's consider a linear polynomial 2x plus 5. Here x is the variable with 2 as its coefficient and 5 is the constant term. Now, let's find the zero of this polynomial. The zero of a polynomial is defined as any real number k, for which the value of the polynomial becomes 0. Let's assume that for x equal to alpha, the value of p of x becomes 0. Thus, p of alpha is equal to 0. This implies that 2 alpha plus 5 is equal to 0. On simplification, we get the value of alpha as minus 5 divided by 2. Here you observe that the numerator 5 is the constant term of the polynomial, and the denominator 2 is the coefficient of the variable x. Based on this observation, we can conclude that the zero of a linear polynomial is equal to the minus of the constant term divided by the coefficient of x. Now, let's consider the general form of the linear polynomial p of x is equal to ax plus b, where a is not equal to 0. Recall that a linear polynomial can have a maximum of 1 zero. Let's assume that alpha is the zero of the linear polynomial ax plus b. Hence, we can say that p of alpha is equal to 0. This implies that a multiplied by alpha plus b is equal to 0. On simplifying this expression, we get alpha is equal to minus b divided by a. Here b is the constant term and a is the coefficient of the variable x of the linear polynomial. This equation defines the relationship between the zero and the coefficient of the linear polynomial. Next, we'll discuss the relationship between the zeros of quadratic and cubic polynomials with its coefficients. Let's consider the general form of the quadratic polynomial. Recall that a quadratic polynomial can have a maximum of 2 zeros. Let's assume that the zeros of the polynomial p of x are alpha and beta. Here we will apply the factor theorem to determine the factors of p of x. Recall that the factor theorem states that if a is a zero of a polynomial p of x, then x minus a is a factor of p of x. In case of a quadratic polynomial, if alpha and beta are zeros of the polynomial p of x, then the factors of p of x are x minus alpha and x minus beta. Thus, the quadratic polynomial is equal to k multiplied by x minus alpha multiplied by x minus beta, where k is a constant not equal to 0. Let's multiply the factors on the right-hand side of the equation. The equation obtained is as shown. Now, let's compare the coefficients on both the sides of the equation. A is equal to k. This is by comparing the coefficient of x square. Let this be equation 1. B is equal to minus k multiplied by alpha plus beta. This is by comparing the coefficient of x. Let this be equation 2. And C is equal to k multiplied by alpha multiplied by beta. Let this be equation 3. Now, let us use the equation 1 and equation 2 to get this relation. This equation indicates that the sum of the zeros is equal to minus b divided by a. Here b is the coefficient of x and a is the coefficient of x square. Therefore, this equation establishes the relationship between the sum of zeros and coefficients of the quadratic polynomial. On using equation 1 and equation 3, we get the product of zeros, which is equal to c divided by a. Here c is the constant term and a is the coefficient of x square. Therefore, this equation defines the relationship between the product of zeros and the coefficients of a quadratic polynomial. Next, let's consider the general form of the cubic polynomial. Let's assume the zeros of a cubic polynomial p of x are alpha, beta, and gamma. Based on the factor theorem, if alpha, beta, and gamma are zeros of p of x, then the factors of p of x are x minus alpha, x minus beta, and x minus gamma. As we have seen in the quadratic polynomial, the cubic polynomial is equal to the product of its factors. Let's simplify and rearrange the right-hand side of the equation. Now, we'll compare the coefficients of x, x square, x cube, and the constant term. A is equal to k. Let this be equation 1. B is equal to minus k into the sum of zeros, alpha, beta, and gamma. Let this be equation 2. C is equal to k into the sum of the product of zeros taken 2 at a time. Let this be equation 3. D is equal to minus k into the product of the zeros. Let this be equation 4. Using equation 1 and 2, we get the sum of zeros is equal to minus b divided by a. Here b is the coefficient of x square and a is the coefficient of x cube. Therefore, This equation defines the relationship between the sum of zeros and the coefficients of the cubic polynomial. Next, by using equation 1 and 3, we get the sum of the product of zeros taken 2 at a time is equal to c divided by a. Here c is the coefficient of x and a is the coefficient of x cube. Therefore, this equation defines the relationship between the sum of the product of zeros taken 2 at a time and the coefficients of the cubic polynomial. Similarly, using equation 1 and 4, the product of zeros is equal to minus d divided by a. Here d is the constant term and a is the coefficient of x cube. Therefore, this equation establishes the relationship between the product of zeros and the coefficients of the cubic polynomial. You have reached the end of this section. Before moving on to the next section, let's recap the key points covered. The zero of a linear polynomial is equal to the minus of its constant term divided by the coefficient of x. If alpha and beta are the two zeros of a quadratic polynomial, then the sum of the zeros of a quadratic polynomial is equal to the minus of the coefficient of x divided by the coefficient of x squared. And the product of the zeros of a quadratic polynomial is equal to the constant term divided by the coefficient of x squared. If alpha, beta and gamma are the three zeros of a cubic polynomial, then the sum of the zeros of a cubic polynomial is equal to the minus of the coefficient of x squared divided by the coefficient of x cubed. The sum of the product of zeros taken 2 at a time of a cubic polynomial is equal to the coefficient of x divided by the coefficient of x cubed. And the product of the zeros of a cubic polynomial is equal to the minus of a constant term divided by the coefficient of x cubed. Hope you enjoyed this learning experience. Welcome to the lesson on the division algorithm for polynomials. At the end of this lesson, you will be able to divide one polynomial by another polynomial. You will also be able to state and verify the division algorithm for polynomials. Let's perform a simple division of 36 by 5. Notice that the quotient is 7 and remainder is 1. We can recall Euclid's division algorithm here. That is, the dividend is equal to the divisor into the quotient plus the remainder. In this case, 36 is equal to 5 into 7 plus 1. Suppose we have polynomials as the dividend and divisor. To perform the division, first we arrange the terms of dividend and divisor in decreasing order of their degrees. Thus, the dividend becomes x cubed minus 6x squared plus 12x minus 8. Let's perform the division. First, we'll divide the first term of the dividend, x cubed, by the first term of the divisor, x squared. We get x. This is the first term of the quotient. We multiply the divisor with the first term of the quotient and subtract this product from the dividend. That is, we multiply x squared minus 3x plus 2 with x and subtract the product x cubed minus 3x squared plus 2x from the dividend. The remainder is minus 3x squared plus 10x minus 8. Now, this remainder is our new dividend. The divisor is the same. To get the second term of the quotient, divide the first term minus 3x squared of the new dividend by the first term x squared of the divisor. so we get minus 3 as the second term of the quotient. Multiplying the divisor with the second term of the quotient and subtracting the product minus 3x square plus 9x minus 6 from the dividend gives x minus 2 as the remainder. Now, x minus 2 is our new dividend and the divisor is x square minus 3x plus 2. Can you perform further division? Let's see. In order to get the third term of the quotient, we divide the first term, x of the new dividend, by the first term of the divisor, x square. On division, we get 1 divided by x, which is not a polynomial. Thus, this cannot be the third term of the quotient. Therefore, further division is not possible. Here the degree of the remainder, x minus 2, is 1, but the degree of the divisor is 2. This implies that division is not possible if the degree of the remainder is less than the degree of the divisor. In general, the division algorithm for polynomials states that if f of x and g of x are the polynomials such that the degree of f of x is greater than or equal to the degree of g of x, where g of x is not equal to 0, then there exists unique polynomials q of x and r of x such that f of x is equal to g of x into q of x plus r of x, where r of x is equal to 0 or the degree of r of x is less than the degree of g of x. This is known as the division algorithm for polynomials. Let's now verify the division algorithm for a polynomial division just performed. Here you have divided x cubed minus 6x square plus 12x minus 8 by x square minus 3x plus 2. On performing the division, the quotient is x minus 3 and the remainder is x minus 2. Now, we'll substitute the values of the divisor, the quotient and the remainder in the algorithm. Let's simplify this. We get x cubed minus 6x square plus 12x minus 8. This is the dividend that we have taken. Hence, we have verified that the division algorithm holds true for polynomial divisions. You have reached the end of this section. Let's recap the division algorithm for polynomials, which states that if f of x and g of x are the polynomials such that the degree of f of x is greater than or equal to the degree of g of x, where g of x is not equal to 0, then there exists unique polynomials q of x and r of x such that f of x is equal to g of x into q of x plus r of x, where r of x is equal to 0 or the degree of r of x is less than the degree of g of x. Hope you enjoyed this learning experience. Welcome to the lesson on the graphical method of solution. At the end of this lesson, you will be able to define the general form of a pair of linear equations in two variables and solve the equations graphically. You will also be able to state the conditions for a pair of linear equations in two variables to have solutions. In everyday life, you will find many things that share a one-to-one relationship with each other. For example, the harder a ball is kicked, the further it will go. Other examples include the quantity and cost of things. 5 balls will cost more than 2 balls. The age and the height. As a baby grows, her height increases. The altitude and the temperature. As you go higher, the temperature decreases. Such relationships are linear in nature and can be expressed mathematically as a pair of equations in two variables. In this lesson, we'll discuss how a pair of linear equations in two variables can be represented and solved graphically. Let's see how. Let's begin by defining the general form of a pair of linear equations in two variables. Consider an example. Mekong wants to know the new taxi tariff. A taxi tariff plan has two components: the fixed minimum fare and the variable fare that is based on the distance covered in kilometers. For a distance of 10 kilometers, he has paid a fare of 115 rupees. And for a distance of 15 kilometers, he has paid a fare of 165 rupees. Let's assume that the fixed minimum fare is X rupees and the variable fare is Y rupees. Here X and Y represent the ordered pair. Based on the given data, the first equation is X plus 10Y is equal to 115. And the second equation is X plus 15Y is equal to 165. These two equations can also be written as follows. Based on these equations, we can write the general form of a pair of linear equations in two variables as a1x plus b1y plus c1 is equal to 0 and a2x plus b2y plus c2 is equal to 0, where a1, a2, b1, b2, c1 and c2 are all real numbers, and a1 square plus b1 square is not equal to 0, and a2 square plus b2 square is not equal to 0. Now, can we represent this pair graphically? Recall that a linear equation in two variables, when plotted on a graph, defines a line. So this means when a pair of linear equations is plotted, two lines are defined. Now, we know that two lines in a plane can intersect each other, be parallel to each other, or coincide with each other. Do these conditions apply to the graphical representation of a pair of linear equations in two variables? Let's plot this pair of equations to understand this. In order to plot the linear equations in two variables, we will have to find at least two ordered pairs for each of the linear equations. Let's consider equation 1. Next, we'll regroup the equation such that y is the subject, or y is on the left-hand side of the equation. Let's call this equation 3. Now, by taking values for x and substituting them in equation 3, we can obtain the corresponding values for y. In this case, we're taking the values of x as -5 and 5. You must be wondering why we have chosen these values. Adding and subtracting 5 will make the numerator divisible by the denominator. So, you will have to do a little bit of analysis before deciding the values you want to substitute. Let's substitute -5 for x in the equation and solve it. The value obtained for y is 12. So the first ordered pair is -5, 12. Next, we'll substitute 5 for x and solve the equation. The value obtained for y is 11. Hence, the second ordered pair is 5, 11. The two ordered pairs for equation 1 are -5, 12 and 5, 11. Similarly, the second equation can be rearranged such that y is the subject. This is equation 4. Here the values for x are taken as -15 and 15. Substituting these values for x in the equation and solving it, we get the values of y as 12 and 10 respectively. Therefore, the two ordered pairs for the second equation are -15, 12 and 15, 10. Now, let's plot the ordered pairs for the first equation. We'll get a straight line. Similarly, on plotting the ordered pairs for the second, we get another straight line. As you can see, the two lines intersect each other at 15, 10. This is the solution of the two equations. It implies x is equal to 15 and y is equal to 10. Thus, the fixed component of the fare is 15 rupees and the variable component is 10 rupees. As discussed, when any pair of linear equations in two variables is plotted, two straight lines are obtained. These lines may either intersect each other or be coincident with each other. These lines can also be parallel to each other. Each of these conditions will determine the solution of the equations. Let us look at the first condition where the two lines are intersecting each other. This is possible only if a1 divided by a2 is not equal to b1 divided by b2. Then the pair of linear equations will have a unique solution. Consider the pair of linear equations given here. Here a1 is equal to 2, b1 is equal to 4, a2 is equal to 1, and b2 is equal to -3. On substituting these values in the condition, we get 2 upon 1 is not equal to 4 upon -3. Here the pair of linear equations will have a unique solution. This means that the lines representing these equations intersect only at one point. Next, let's consider the second case where the lines coincide with each other. This condition is possible only if a1 upon a2, b1 upon b2, and c1 upon c2 are equal. In this case, the pair of linear equations will have infinite solutions. Consider the pair of linear equations given here. On substituting the values of a1, a2, b1, b2, c1, c2 in the condition, you get 1 upon 2 is equal to 1 upon 2, which is also equal to 1 upon 2. This pair of linear equations have infinite solutions. A pair of linear equations which has a unique or infinite solutions are said to be consistent pair of linear equations. See, the lines represented by the linear equations are coincident here. A pair of linear equations, when plotted, may define lines that neither intersect nor coincide. These lines are parallel to each other. Such a situation is possible only if a1 upon a2 is equal to b1 upon b2, which is not equal to c1 upon c2. Here the pair of linear equations has no solution. Such a pair of linear equations is said to be inconsistent. Let's look at an example of an inconsistent pair of linear equations. On substituting the values of a1, a2, b1, b2, c1 and c2, you get 1 upon 2 is equal to 1 upon 2, which is not equal to -6 upon -5. As you can see, these lines are not intersecting. You have reached the end of this section. Before moving on to the next section, let's recap the key points covered. Two linear equations in the same two variables are called a pair of linear equations in two variables. The most general form of a pair of linear equations is a1x plus b1y plus c1 is equal to 0. a2x plus b2y plus c2 is equal to 0, where a1, a2, b1, b2, c1, c2 are real numbers, such that a1 square plus b1 square is not equal to 0, a2 square plus b2 square is not equal to 0. The graph of a pair of linear equations in two variables is represented by two lines. If the lines intersect at a point, then that point gives the unique solution of the two equations. In this case, the pair of equations is consistent. If the lines coincide, then there are infinitely many solutions, as each point on the line is a solution. In this case, the pair of equations is consistent. If the lines are parallel, then the pair of equations has no solution. In this case, the pair of equations is inconsistent. Welcome to the lesson on algebraic methods of solving a pair of linear equations. At the end of this lesson, you will be able to solve a pair of linear equations using three algebraic methods: the substitution method, the elimination method, and the cross multiplication method. You will also be able to solve a pair of non-linear equations which can be represented as linear equations. You have learned how to find the solutions of a pair of linear equations graphically. However, this method may not always give the most accurate solutions, especially when the point representing the solution has non-integral coordinates like square root 2, square root 3, or 1 divided by 3, minus 5 divided by 4. Identifying such coordinates can be quite a challenge. So, how do we solve such equations? Algebraically, of course. There are three algebraic methods that can be used to solve a pair of linear equations. Now, recall that a pair of linear equations in two variables can either have a unique solution and infinite solutions, or no solution. To verify this, we can compare the ratios of the coefficients of the x and the y variables. Consider the standard form of a pair of linear equations in two variables. If a1 divided by a2 is not equal to b1 divided by b2, then there will be a unique solution. If a1 divided by a2 is equal to b1 divided by b2 is equal to c1 divided by c2, then there will be infinite solutions. If a1 divided by a2 is equal to b1 divided by b2 is not equal to c1 divided by c2, then there will be no solution. Let's begin with the substitution method. Consider the pair of linear equations x minus y is equal to 5 and x plus 2y is equal to 20. The first step to solve a pair of linear equations by the substitution method is to solve one equation for either of the variables. In other words, we can solve for either x or y in either equation 1 or equation 2. The choice of equation or variable in a given pair does not affect the solution for the pair of equations. To keep it simple, choose the equation and variable that can be solved quickly without complication. Looking at these two equations, we can see that rearranging equation 1 to make x as the subject is simpler. So, we solve for x in equation 1. We have x is equal to 5 plus y. In the next step, we'll substitute the resultant value of one variable obtained in the other equation and solve for the other variable. Here we'll substitute the value of x, which is equal to 5 plus y in equation 2. Let's solve this equation further. Hence, the value of y is equal to 5. In the last step, we can substitute the value obtained of the variable in any one equation to find the value of the second variable. So, here we'll substitute the value of y, which is equal to 5 in equation 1. Let's solve this equation. Hence, the value of x is equal to 10. Therefore, the solution to the given pair of linear equations is x is equal to 10 and y is equal to 5. The solution can be verified by substituting the values of x and y in both the equations. Let's check this out. In equations 1 and 2, substituting x is equal to 10 and y is equal to 5. We can see that both the equations are satisfied. Next, we'll learn another algebraic method, the elimination method to solve a pair of linear equations. The elimination method, as the name suggests, involves elimination of one variable by equating the coefficients of that variable in both the equations. Consider the pair of linear equations 5x minus 2y is equal to 14 and 3x plus 5y is equal to 120. In this method, the first step involves multiplying the equations with suitable non-zero constants so that the coefficients of one variable in both equations become equal. Here we'll multiply the first equation by 5 and the second equation by minus 2. By doing this, the coefficients of y in both the equations becomes minus 10. Please note that minus 2 and 5 are the coefficients of y in equation 1 and 2 respectively. The next step is to subtract one equation from another to eliminate the variable with equal coefficients. In this case, we'll subtract. So, we now subtract the fourth equation from the third equation. This eliminates the variable y and leaves the equation with just one variable. Now we solve the equation to get the value of the remaining variable, that is, x. Solving, we get x is equal to 10. The next step is to substitute the obtained value of the variable in one of the equations and solve for the second variable y. Substituting x is equal to 10 in equation 1 and solving. We get y is equal to 18. Therefore, the solution to the given pair of linear equations is x is equal to 10 and y is equal to 18. Let us verify the solution by substituting the values of x and y in both the equations. Substituting x is equal to 10 and y is equal to 18 in equations 1 and 2. We see that both the equations are true. In this pair of linear equations, we have obtained a unique solution for the pair of equations. We will now discuss the third method of solving a pair of linear equations, the cross-multiplication method. Let's consider the general form of a pair of linear equations. a1x plus b1y plus c1 is equal to 0. and a2x plus b2y plus c2 is equal to 0. Recall that when a1 divided by a2 is not equal to b1 divided by b2, the pair of linear equations will have a unique solution. To solve this pair of equations for x and y using cross multiplication, we'll arrange the variables x and y and their coefficients a1, a2, b1 and b2 and the constants c1 and c2 as shown on the screen. Now, we write x divided by the product of b1 and c2 minus the product of b2 and c1. Following the same procedure for y and 1 and equating the three fractions, we get the expression as shown here. Now, let us try this method on equations we have earlier solved using the elimination method. Let's rewrite the equations in standard form. Now, let's compare the ratio of the coefficients of x and y. It is not equal, which implies that the equations have a unique solution. Now, let us apply the cross multiplication method and solve the equations. We get x is equal to 10 and y is equal to 18. The solution obtained is the same as the solution obtained by using elimination method. We can use any of these three methods to solve a pair of linear equations. However, the trick is to use the method that is simple and convenient. Consider this pair of equations. These equations are not linear. So, how do we solve such equations? Equations like these can be reduced to linear equations. Let's see how. First, we'll rewrite the equations as shown. Next, we'll substitute the fraction 1 divided by x plus 2 with u and the fraction 1 divided by y minus 2 with v respectively. So the two variables in the pair of linear equations are u and v. Now, using any of the three methods, we can solve for u and v in this pair of linear equations. Let's use the elimination method. Observe that the coefficients of v in both the equations are same. So we can eliminate v by subtracting equation 4 from equation 3. Simplifying, we get u is equal to 1 divided by 7. Now substituting the value of u in equation 4 and solving, we get v is equal to 1. We know 1 divided by x plus 2 is equal to u, and 1 divided by y minus 2 is equal to v. Now we substitute the values of u and v in 1 divided by x plus 2 and 1 divided by y minus 2 and solve for x and y. Therefore we get x is equal to 5 and y is equal to 3. Let's substitute x is equal to 5 and y is equal to 3 in equations 1 and 2. Next, we'll simplify the equations. As you can see, the linear equations are satisfied. Thus we have verified. So, we can solve for any pair of nonlinear equations if such equations can be represented as a pair of linear equations. Let's begin with a problem. Suppose the difference between the present ages of Tom and Harry is 6 years. 10 years later, the product of their ages will be 280. How old are Tom and Harry now? In this lesson, you will learn about quadratic equations and different methods of solving them. At the end of this lesson, you will be able to define a quadratic equation, solve a quadratic equation using one of the following methods: factorization, converting into perfect square, quadratic formula, and graphical representation. As per the problem, let us assume that Tom's present age is x years, so Harry's present age will be 6 plus x years. According to the problem, 10 years later, Tom's age will be x plus 10 years, and Harry's age will be 6 plus x plus 10 years, which is equal to 16 plus x years. Additionally, it is given that the product of their ages will equal to 280. Thus, x plus 10 times 16 plus x is equal to 280. On solving the equation, you get x squared plus 26x minus 120 is equal to 0. Equations where the degree of the variable is 2 are called quadratic equations. A quadratic equation is a polynomial where the highest degree of a variable is 2. The general form of quadratic equation in one variable is ax squared plus bx plus c is equal to 0, where a, b and c are real numbers. A is not equal to 0. The values that satisfy a quadratic equation are known as zeros. roots or solutions of that quadratic equation. There are 4 methods of solving a quadratic equation: factorization, completing the squares, quadratic formula, and graphical representation. We'll look at each of these methods in detail through the scenario about Harry and Tom's present ages. Let us first use the factorization method to solve the given problem. Consider the quadratic equation x squared plus 26x minus 120 is equal to 0. To solve this problem, you need to find x in the quadratic equation. You can do this in a number of steps. Step 1. Multiply the first and the last term of the equation. The product of the first and the last term is equal to minus 120 x squared. Step 2. Find the factors of minus 120 x squared in such a way that when you add them, the sum or the difference is equal to the middle term 26x. In this case, the factors are 30x and minus 4x. Step 3. Take a common factor x from the first 2 terms and minus 4 from the last 2 terms. You get x times x plus 30 minus 4 times x plus 30 is equal to 0. Step 4. Take x plus 30 as the common factor from the equation. Your equation becomes x plus 30 times x minus 4 is equal to 0. Thus, the roots of the quadratic equation are minus 30 and 4. As a person's age cannot be negative, the solution to the problem is 4. Therefore, Tom's present age is 4 years, and Harry's present age is 6 plus x is equal to 6 plus 4 is equal to 10 years. There may be problems where you find it difficult to determine the factors of the equation x squared plus 2x plus 2. In such cases, you can use another method to solve quadratic equations. This method involves the converting of the equation into perfect squares. Let's verify this method by taking up again the quadratic equation x squared plus 26x minus 120 is equal to 0. Step 1. Bring the constant value minus 120 to the right-hand side of the equation. The resultant equation is x squared plus 26x is equal to 120. Step 2. Divide the second term 26x into 2 equal parts. Each part is 13x. The diagram shows the corresponding changes. Step 3. The next step involves making the equation a perfect square. Add 13 square on both sides of the equation. You get x squared plus 2 times x times 13 plus 13 squared is equal to 120 plus 13 squared. On simplifying the equation, you get x plus 13 is equal to plus or minus 17. This means x plus 13 is equal to minus 17 or x plus 13 is equal to 17. Hence the values of x are minus 30 and 4. Therefore, the answer to the problem is Tom's age is equal to x is equal to 4 years. Harry's age is equal to 6 plus x years is equal to 6 plus 4 is equal to 10 years. Sometimes it may be difficult to find the factors in a quadratic equation or transform the equation into a perfect square. In such cases, you can use the quadratic formula to solve the problem. To derive the quadratic formula, let's start with the general form of a quadratic equation. ax squared plus bx plus c equals 0. Step 1. Bring the constant c to the right side of the equation. You get ax squared plus bx equals minus c. Step 2. Divide both sides of the equation with the coefficient of x squared, that is, a. You get x squared plus b times x divided by a is equal to minus c divided by a. Step 3. Multiply and divide the last term by 2 to get the equation in terms of 2ab. The result is x squared plus product of 2x and b divided by 2a is equal to minus c divided by a. Step 4. You need to convert the equation into the form of identity. A plus b whole squared is equal to a squared plus 2ab plus b squared. To do this, add b divided by 2 times a whole squared on both the sides. Now you have x squared plus product of 2x and b divided by 2 times a plus b divided by 2 times a whole squared is equal to minus c divided by a plus b divided by 2 times a whole squared. On solving the equation, you get x is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. Therefore, the roots of this quadratic equation are x is equal to minus b minus square root of b squared minus 4ac divided by 2a and x is equal to minus b plus square root of b squared minus 4ac divided by 2a. Now you can try applying the derived quadratic formula to find the ages of Tom and Harry. First compare the quadratic equation x squared plus 26x minus 120 equals 0 with the general form of a quadratic equation, which is ax squared plus bx plus c is equal to 0. You get a is equal to 1, b is equal to 26, and c is equal to minus 120. The quadratic formula is x is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. On substituting the values of a, b and c in the formula, you get x is equal to minus 26 plus or minus square root of 26 squared minus 4 times 1 times minus 120 divided by 2 times 1. On simplifying, you get x is equal to minus 30 or x is equal to 4. Therefore, as you can see, using the quadratic formula, you can verify the answer to the problem. Tom's age is equal to x is equal to 4 years. Harry's age is equal to 6 plus x years is equal to 6 plus 4 is equal to 10 years. Using the quadratic formula gives you certain advantages over other methods. Without actually solving the equation, the formula enables you to calculate the sum of the roots and the product of the roots. Now let's look at the sum of the roots Let us consider the roots as alpha and beta respectively. Alpha equals minus b minus square root of b squared minus 4ac divided by 2a, and beta equals minus b plus square root of b squared minus 4ac divided by 2a. Therefore, the sum of the roots of a quadratic equation is alpha plus beta equals minus b minus square root of b squared minus 4ac divided by 2a plus minus b plus square root of b squared minus 4ac divided by 2a. On simplification, you get alpha plus beta is equal to minus b divided by a. Thus, sum of roots is equal to minus x coefficient divided by x squared coefficient. Now, let's look at the product of the roots. The product of the roots of a quadratic equation is alpha times beta equals minus b minus square root of b squared minus 4ac divided by 2a times minus b plus square root of b squared minus 4ac divided by 2a. On simplification, you get alpha times beta equals c divided by a. That is, product of roots is equal to constant term divided by x squared coefficient. Let's again refer to the problem about Tom and Harry's present ages and use it to find the sum and products of the roots. X squared plus 26x minus 120 equals 0. On comparing the given equation to the general form of quadratic equation, you get a is equal to 1, b is equal to 26, and c is equal to minus 120. Now, apply the sum of roots formula. Alpha plus beta is equal to minus b divided by a. On substituting the values of b and a in the formula and simplifying, you get the sum as minus 26. Similarly, on applying the formula for product of roots, alpha times beta is equal to c divided by a, and simplifying, you get the product of roots is equal to minus 120. The roots obtained depend on b squared minus 4ac, which is known as the discriminant of the quadratic equation and is denoted by d or delta. You can use the discriminant to find out the nature of the roots that represent the answer to your problem. You can determine the nature of each root without solving the quadratic equation. If d is greater than 0, then the roots are real and distinct or unequal. If d is less than 0, then the roots are imaginary. If d is equal to 0, then the roots are real and equal. For example, let's consider the roots for the equation x squared plus 26x minus 120 is equal to 0. On comparing the given equation with the general form of a quadratic equation, you get a is equal to 1, b is equal to 26, c is equal to minus 120. Substituting the values of a, b and c in the formula and simplifying, you get d is equal to 1156. Since d is greater than 0, the roots are real and distinct. As mentioned earlier, you can also solve quadratic equations graphically. Let us consider the graphical representation method to find Tom and Harry's present ages. The quadratic equation is x squared plus 26x minus 120 is equal to 0. Let's assume y is equal to x squared plus 26x minus 120. As you can see, the table displays a list of ordered pairs based on the equation y is equal to x squared plus 26x minus 120. On plotting the ordered pairs on a graph, the curve of the quadratic equation y is equal to x squared plus 26x minus 120 emerges as a parabola. This parabola intersects the x-axis at minus 30, 0 and 4, 0. Since this parabola touches the x-axis at minus 30 and 4, the roots of the quadratic equation are minus 30 and 4. Therefore, Tom's age is equal to x is equal to 4 years. Harry's age is equal to 6 plus x years is equal to 6 plus 4 is equal to 10 years. The curve of the parabola varies based on the value of the coefficient of x squared, that is a, the discriminant b squared minus 4ac. Let's look at the impact of each of these factors on the parabola. First, let's consider the value of a. In a quadratic polynomial, ax squared plus bx plus c. If the value of a is greater than 0, then the parabola opens upward. If the value of a is less than 0, then the parabola opens downward. Now, let's look at the impact of the discriminant on the parabola. If the discriminant value is greater than 0, then the parabola intersects the x-axis at two different points. If the discriminant value is less than 0, then the parabola does not intersect the x-axis. If the discriminant value is equal to 0, then the parabola intersects the x-axis at only one point. In our daily lives, we can observe patterns in natural as well as man-made objects. For instance, look at the child playing with his toy pyramid set. How many bricks will he need to finish the pyramid with one brick at the top? How many bricks will he have in the fourth row? Not too difficult to determine, is it? However, consider a situation where the pyramid is much higher, maybe 200 bricks. How many bricks would the child need for the 54th row? It's a little more difficult to figure out, right? You may often need to make such calculations, whatever field you choose to work. For example, in construction activities or even in financial matters, you will need to work with patterns. You need to learn to analyze and predict patterns, also called progressions, to be able to resolve such problems. Progression can be arithmetic, geometric, or harmonic. In this lesson, you will learn about arithmetic progression. At the end of this lesson, you will be able to identify an arithmetic progression or AP, define arithmetic progression, calculate the common difference of an AP, and derive and apply the formula for general term. To understand progression, take take a look at some sequences. For example, consider the sequence 2, 4, 6, 8, and so on. You need to predict the fifth term in this sequence. If you analyze this sequence, you will find a constant between every two successive terms in the sequence. For instance, 4 equals 2 plus 2, 6 equals 2 plus 4, 8 equals 2 plus 6. As you can see, the constant is 2. Therefore, fifth term equals constant plus fourth term, which is 10 equals 2 plus 8. Now, let us look at another sequence with fractions. -1 upon 2, 0, 1 upon 2, 1, and so on. In this sequence, the constant is 1 upon 2. Consider the following sequences 4, 9, 11, 13, and so on, and -8, -5, 0, 1, and so on. You can see that there is no constant between the terms in either of these sequences. Based on this data, it will not be possible to obtain the next term in any of these sequences because there is no visible pattern. The pattern in the first two examples shows that you can obtain successive terms by adding a fixed number or a constant to the preceding terms. Such a list of numbers is said to form an arithmetic progression. So, an arithmetic progression, or AP, is a sequence of numbers or terms in which each term is obtained by adding a constant to the preceding term. This fixed number or constant is called the common difference of the arithmetic progression. It is represented by D. Now remember, if D is not constant, then the sequence is not an AP. D can be a positive number, negative number, or 0. Consider the following problems regarding arithmetic progression. Find the sixth term in the sequence 2, 4, 6, 8, and so on. Find the 13th term in the sequence -15, -11, -7, -3, and so on. John is saving money in a bank. He deposits 100 rupees in the first week. Later, he deposits 25 rupees in the account every week. What will be the amount in his account at the end of the 20th week? It is easy to find the sixth term in the sequence in problem 1. However, problem 2 and 3 typically may take you a while to work out. To solve such problems quickly and easily, you can derive a formula to determine the general term, that is, the nth term or the last term in a sequence. Let us consider problem 3. After saving 100 rupees in the first week, John saves 25 rupees every week. Therefore, the common difference, D, in John's savings every week is 25. Thus, the balance in John's account is 100 in the first week, 100 plus 25 in the second week, 100 plus 2 multiplied by 25 in the third week, and so on. Let John's savings in the first week, that is, the first term in the sequence, be A. In this problem, 100 equals A. The common difference, 25, equals D. As you can see from the table, the general form of AP is A plus D, A plus 2D, and so on. If you denote the first term, A, as T1, the second term, A plus D, as T2, the third term, A plus 2D, as T3, and so on, then you get T2 equals A plus 2 minus 1 multiplied by D, and T3 equals A plus 3 minus 1 multiplied by D. You can generalize this to get the 20th term, which is A plus 20 minus 1 multiplied by D. Therefore, T20 equals 100 plus 20 minus 1 multiplied by 25. On solving, you get T20 as 575. In other words, you come to know that John's total savings in the 20th week will be 575 rupees. T20 equals 100 plus 20 minus 1 multiplied by 25. If you substitute 20 with n in the above calculation, you will get a general formula for calculating the nth term of an AP. Thus, Tn equals a plus n minus 1 multiplied by d, where Tn equals last term of the progression, a equals first term, d equals common difference. The number of terms of an arithmetic progression whose a, d and Tn are given is n equals to Tn minus a divided by d plus 1. A mason is laying bricks for a narrow staircase. For every step, he needs to add 4 bricks to the previous step. The staircase requires 25 steps. If you were to order the bricks for the mason, how would you determine the total number of bricks required for the staircase? In this lesson, you will learn how to calculate the sum of n terms in an AP. At the end of the lesson, you will be able to derive the formula for the sum of n terms in an arithmetic progression, also called AP. Apply the formula to calculate the sum of n terms in a given problem. APs display an interesting property that can help us derive a generic formula for calculating the sum of n terms. Take an example of a sequence of numbers 2, 4, 6, 8, 10, and 12. If you add the first term 2 to the last term 12 in the sequence, the sum of the two terms equals 14. Similarly, if you add the second term to the fifth term and the third term to the fourth term, you get 4 plus 10 equals 14. 6 plus 8 equals 14. As you can see, the result of these additions is equal. This property can be observed in all APs, including reverse APs. For example, if you reverse the given AP, you get 12, 10, 8, 6, 4, 2. Now try adding the first and the last terms of this AP, that is 12 and 2. The sum is 14. Similarly, if you add the second term to the fifth term and the third term to the fourth term, the sum is 14. This shows a pattern that we can use to derive a formula for the sum of n terms. In a standard arithmetic sequence where a equals first term, d equals common difference, and n equals number of terms, the second term will be a plus d, and so on. In this way, you can compute each term till the nth term. Let the sum of these terms be s. Now, let's consider the reverse of this AP. In the reversed AP, the last term, a plus n minus 1 multiplied by d, appears in the first position, and the first term, a, in the last position. The sum of the terms of this AP also will be s. Now add the corresponding terms of both the APs, that is, first term to first term, second term to second term, and so on. While calculating, you will find that the sum of the corresponding terms are equal in every case. Thus, we get 2a plus n minus 1 multiplied by d in every case. As there are n terms, the total sum will be equal to n multiplied by 2a plus n minus 1 multiplied by d. As we are adding the two APs, the sum of n terms will be doubled, that is, it becomes 2s. So, to get s, that is the sum of n terms of an AP, you have to divide the equation by 2. Thus, you get the formula for s. S equals n divided by 2 multiplied by 2a plus n minus 1 multiplied by d. On further simplification, you get the sum of n terms in an AP, S equals n divided by 2 multiplied by the first term plus last term. Remember the Mason's problem? Using the formula for the sum of n terms, you can now determine the number of bricks to be ordered for the staircase. You can see that the number of bricks in the staircase forms an AP. According to the given data, the first step will have 4 bricks. Therefore, the first term A equals 4. Common difference D is 4, and the total number of steps in the staircase equals the number of terms in the progression, n, which is 25. You can apply the formula for sum of n terms to the given data. Substituting the values of n, A, and D in the formula, you get the value for the sum of n terms, S. After simplifying, you get S equals 1300. Therefore, the mason requires a total of 1300 bricks to construct a staircase of 25 steps. Welcome to the lesson on similarity. At the end of this lesson, you'll be able to identify similar figures and differentiate between congruent and similar figures. You will also be able to identify the conditions that define similarity of triangles and prove the basic proportionality theorem and its converse. You must be wondering why we're in a sports room during a geometry session. Well, there is geometry all around us. Let's try to find some here. Look at the different types of balls kept here. There's a football, a volleyball, a cricket ball, and a tennis ball. Ah, and here's a golf ball. That's quite a variety. All these balls are spherical in shape. Does this make them congruent? Objects are said to be congruent only if they are of the same shape and the same size. For example, look at these hockey sticks. They are equal in shape and size. Hence, they are congruent. As for the balls, though they are of the same shape, their sizes differ. Objects that are of the same shape but differ in size are said to be similar. Let's recap the definitions of congruent and similar objects. Congruent objects have the same shape and size, while similar objects have the same shape but may not necessarily have the same size. An important observation to note is that all congruent figures are similar, but all similar figures need not be congruent. Now, consider the geometrical figures given here. Let's sort the figures on the basis of similarity. Here, now all similar figures are aligned together. Let's analyze these figures to further understand similarity. All circles are of the same shape and their radii will always be proportional. Hence, all circles are similar. All squares are similar to each other as their angles are equal and their corresponding sides are proportional. Using the same logic, all rectangles are similar as the angles are equal and two pairs of corresponding sides are proportional. Now, let's check the similarity of triangles. On measuring the angles, we find that the corresponding angles are equal. On measuring the lengths of the corresponding sides, we find that the three pairs of corresponding sides are proportional. For two triangles to be similar, the corresponding angles must be equal, and the length of the corresponding sides must be proportional. To better understand the property of the similarity in triangles, let's perform a small activity. Cut a triangular-shaped piece of cardboard. Let's call this triangle ABC. Now hold it between a light bulb and the wall. Can you see the shadow of the triangle? It is an enlargement or magnification of the cardboard triangle because light propagates in a straight line. Let's mark the shadow of the triangle as A', B', C'. Consider the point of the light bulb as O. Draw rays OA, OB and OC originating from point O. If we extend this ray further, we'll observe that A' lies on ray OA, B' lies on ray OB, and C' lies on ray OC. This means that the triangles ABC and A', B', C' are of the same shape. However, their sizes are different. So we can say that triangle ABC is similar to triangle A', B', C', and vice versa. Mathematically, similarity is represented as shown. Here, vertex A corresponds to vertex A', vertex B corresponds to vertex B', and vertex C corresponds to vertex C'. Symbolically, these correspondences are represented as A', B', B', and C'. Similarly, angle A is equal to angle A', angle B is equal to angle B', and angle C is equal to angle C'. And all pairs of corresponding sides of the triangles are proportional. Note that the same ratio of the corresponding sides is referred to as the scale factor. Next, we will discuss an important theorem based on the similarity of triangles. This theorem is called the basic proportionality theorem or the Thales theorem. The basic proportionality theorem states that if a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, then the other two sides are divided in the same ratio. A triangle ABC is given such that a line drawn parallel to side BC intersects the other two sides AB and AC at points D and E respectively. If we prove that AD upon DB is equal to AE upon EC, then the theorem will also be proved. To prove this theorem, join B to E and C to D. Also draw two perpendiculars, DM on AC and EN on AB. Let's begin the proof. Consider triangle ADE and triangle BDE. The area of a triangle can be calculated as half of the product of the base and the corresponding height. This means the area of triangle ADE is half the product of the base AD and the height EN. Similarly, the area of triangle BDE is half the product of the base DB and the height EN. Now, let's divide the areas of the two triangles. On simplifying, we can see that the area of triangle ADE divided by the area of triangle BDE is equal to side AD divided by side DB. Let's assign this observation as equation 1. Now consider triangle ADE and triangle DEC. The area of triangle ADE can also be calculated as half the product of the base AE and the height DM. The area of triangle DEC is equal to half the product of the base EC and the height DM. Now, let's divide the areas of the two triangles. We can see that the area of triangle ADE divided by the area of triangle DEC is equal to AE divided by EC. Let's assign this observation as equation 2. Consider triangle BDE and triangle CED. The area of triangle BDE is equal to the area of triangle CED because these triangles are on the same base DE and between the same parallels BC and DE. Let's assign this observation as equation 3. From equations 1, 2 and 3, we get the following expression. This implies that the ratio of sides AD and DB is equal to the ratio of sides AE and EC. Thus, the basic proportionality theorem is proved. Now, let's prove the converse of the basic proportionality theorem. The converse of the theorem states that if a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. Consider the figure. A triangle ABC is given. The line DE intersects side AB and AC at points D and E respectively, such that the sides are divided in the same ratio. To prove the theorem, we'll prove that line DE is parallel to side BC. In triangle ABC, AD upon DB is equal to AE upon EC because it is given that line DE intersects the sides AB and AC in the same ratio. Let's assign this observation as equation 1. Let's assume that DE is not parallel to BC. If DE is not parallel to BC, draw a line DE' parallel to BC. Since DE' is parallel to BC, by the basic proportionality theorem, we have AD by DB is equal to AE' by E'(C). Let's assign this observation as equation 2. From equations 1 and 2, we get AE by EC is equal to AE' by E'(C). Let's assign this observation as equation 3. Adding 1 on both sides of 3 and on simplifying, we get EC is equal to E'(C). Therefore, we can say that E and E' coincide. Hence, DE is parallel to BC. Lila is in Egypt on an exchange program sponsored by her school. Everything about Egypt is magnificent, and the pyramids that the Egyptians built around 2500 BC are just mesmerizing. It looks like the Egyptians knew a lot about geometry. How else could they have made such huge similar structures? What amazes her most is the similarity between the pyramids. Now, look at the lateral surfaces of all the pyramids. They are all triangles that are similar to each other. Welcome to the lesson on the criteria for the similarity of triangles. At the end of this lesson, you will be able to prove the AAA, the SSS, and the SAS similarity criterion of triangles. Let's consider two triangles, triangle ABC and triangle DEF. These two triangles are similar. Recall that for two triangles to be similar, two conditions must be met. First, the corresponding angles of the two triangles must be equal. Second, the corresponding sides of the two triangles must be proportional. Now, to prove the similarity of triangles, do we need to prove both the conditions? Actually not. There are three criteria that define the similarity of triangles. These are the AAA, the SSS, and the SAS similarity criteria. Proving any of these criteria is enough to prove that two triangles are similar. Let's discuss these criteria in detail. By the AAA similarity criterion, if the corresponding angles of two triangles are equal, then their corresponding sides are proportional and the triangles are similar. Let's consider two triangles, triangle ABC and triangle PQR. Here angle A is equal to angle P, angle B is equal to angle Q, and angle C is equal to angle R. In order to prove that triangle ABC is similar to triangle PQR, by the AAA similarity criterion, we'll prove that the ratios of sides AB and PQ, AC and PR, and BC and QR are equal. To prove the criterion, we'll mark 2 points, L and M on PQ and PR respectively, such that PL is equal to AB and PM is equal to AC, and then we'll join LM. Now, let's consider triangle ABC and triangle PLM. In these two triangles, by construction, AB is equal to PL and AC is equal to PM. Also as given, angle BAC is equal to angle LPM. Therefore, by the SAS congruence rule, triangle ABC is congruent to triangle PLM. Now, let's consider angle B and angle L. These two angles are equal as their corresponding angles of congruent triangles. It is also given that angle B is also equal to angle Q. Hence, angle L is equal to angle Q. Now, let's consider LQ. Observe that it forms a transversal to LM and QR. Since angles L and Q form a pair of corresponding angles that are congruent, LM is parallel to QR. Next, let's consider sides PL and LQ and sides PM and MR. By the basic proportionality theorem, PL upon LQ is equal to PM upon MR. That means these sides are proportional. Now, let's take the reciprocal of this equation. Let's add 1 to both sides of the equation and simplify it. Here LQ plus PL is equal to PQ and MR plus PM is equal to PR. Through construction, PQ and AB are in the same ratio as PR and AC. Now, let's take the reciprocal of this equation. We'll call this equation 1. Similarly, AB and PQ are in the same ratio as BC and QR. Let's call this equation 2. Equating 1 and 2, we get the ratio of AB and PQ equal to the ratio of AC and PR, which is equal to the ratio of BC and QR. Thus, we have proved both the conditions for the similarity of triangles. Hence, triangle ABC is similar to triangle PQR. We have proved that if the corresponding angles in two triangles are equal, then their corresponding sides are in the same ratio and the triangles are similar. This is the AAA similarity criterion. An important point to note is that when two corresponding angles of two triangles are equal, then the two triangles are similar. This is referred to as the AA similarity criterion. The converse of this theorem defines the second similarity criterion, the SSS similarity criterion. We'll discuss it next. By the SSS criterion, if the sides of one triangle are proportional to the sides of the other triangles, then their corresponding angles are equal and the triangles are similar. Let's consider two triangles, ABC and DEF. Here the ratios of the corresponding sides are equal. In order to prove that the two triangles are similar, we'll prove that the corresponding angles are equal. To prove this criterion, we'll mark 2 points P and Q on DE and DF respectively, such that DP is equal to AB and DQ is equal to AC, and we'll join PQ. Let's consider triangle ABC and triangle DEF. It is given that the ratio of AB and DE is equal to the ratio of AC and DF. Now, by construction, DP is equal to the side AB and side DQ is equal to the side AC. Taking the reciprocal, we can also write the equation as DE upon DP is equal to DF upon DQ. On subtracting 1 from both sides of the equation and simplifying, we get PE upon DP is equal to QF upon DQ. Now taking the reciprocals again, we get DP upon PE is equal to DQ upon QF. By applying the converse of the basic proportionality theorem, PQ is parallel to EF. Since PQ and EF are parallel, angle P is equal to angle E and angle Q is equal to angle F, as they form a pair of corresponding angles. Now, DP upon DE is equal to DQ upon DF, which is equal to PQ upon EF. This can also be written as AP upon DE is equal to AC upon DF, which is equal to PQ upon EF. But AB upon DE is equal to AC upon DF, which is equal to BC upon EF. Therefore, PQ upon EF is equal to BC upon EF. Hence, BC is equal to PQ. In triangles ABC and DPQ, by construction, AB is equal to DP and AC is equal to DQ. Therefore, we will be able to prove that BC is equal to PQ. Hence, triangle ABC and triangle DPQ are congruent by the SSS congruence rule. So now angle A is equal to angle D, angle B is equal to angle P, and angle C is equal to angle Q. Since angle P is equal to angle E and angle Q is equal to angle F, angle A is equal to angle D, angle B is equal to angle E, and angle C is equal to angle F. Therefore, triangle ABC is similar to triangle DEF. We have proved that if the sides of one triangle are proportional to the sides of the other triangles, then their corresponding angles are equal and the triangles are similar. Thus, the SSS similarity criterion is proved. Next, we'll discuss the SAS similarity criterion. By the SAS similarity criterion, if one angle of a triangle is equal to one angle of the other triangle, and the sides including these angles are proportional, then the triangles are similar. Let's consider two triangles ABC and DEF. Here it is given that angle A is equal to angle D, and AB upon DE is equal to AC upon DF. We will prove that triangle ABC and triangle DEF are similar. Let's mark 2 points P and Q on DE and DF respectively, such that the side DP is equal to the side AB and side DQ is equal to the side AC, and we'll join PQ. It is given that the ratio of side AB and DE is equal to the ratio of side AC and DF. Since DP is equal to AB and DQ is equal to AC, this equation can also be written as dP upon dE is equal to dQ upon dF. Now, let's take the reciprocal of this equation. Next, dE can be written as the sum of dP and PE, and dF can be written as the sum of dQ and QF. On simplifying, we get. Now, taking reciprocals again, we get dP upon PE is equal to dQ and QF. By the converse of the basic proportionality theorem, PQ is parallel to EF. Since PQ and EF are parallel, angle P is equal to angle E, and angle Q is equal to angle F, because they are corresponding angles. Now consider triangle DPQ and triangle DEF. Since angle P is equal to angle E, and angle Q is equal to angle F, triangles DPQ and DEF are similar. Let's call this equation 1. In triangle ABC and DPQ, AB is equal to DP and AC is equal to DQ by construction. It is given that angle A is equal to angle D. Therefore, by the SAS congruence rule, triangle ABC and triangle DPQ are congruent. Let's call this equation 2. From equations 1 and 2, we get triangle ABC is similar to triangle DEF. You have reached the end of this section. Before moving on, let's review the key points covered. Two triangles are similar if their corresponding angles are equal and their corresponding sides are in the same ratio or are proportional. If in two triangles the corresponding angles are equal, then their corresponding sides are proportional and the triangles are similar. This criterion is referred to as the AAA, or the angle-angle-angle similarity criterion of triangles. If two corresponding angles of two triangles are equal, then the two triangles are similar. This is known as AA, or the angle-angle similarity criterion of triangles. If in two triangles, the sides of one triangle are proportional to the sides of the other triangle, then their corresponding angles are equal and the two triangles are similar. This criterion is referred to as the SSS, or the side-side-side similarity criterion of triangles. If one angle of a triangle is equal to one angle of the other triangle, and the sides including these angles are proportional, then the two triangles are similar. This criterion is referred to as the SAS, or the side-angle-side similarity criterion of triangles. Hope you enjoyed this learning experience. Welcome to the lesson on the areas of similar triangles. At the end of this lesson, you will be able to prove that the ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. You will also be able to prove that if a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then triangles on both sides of the perpendicular are similar to the whole triangle and to each other. You will also be able to prove the Pythagoras theorem and its converse. In this lesson, we'll discuss three important theorems that are based on the areas of similar triangles. But first, let's review the basics of similar triangle. Consider this scenario. It is mid-morning and Stan and Anita are waiting for their friends in the park. They're both standing beside a lamppost. Stan is getting bored, so he begins quizzing Anita. If the length of Anita's shadow and the length of the shadow of the lamppost are known, can the actual length of the lamppost be calculated? Anita's shadow measures 10 feet, while her actual height is only 5 feet. The shadow of the lamppost is 30 feet. Let's assume that the height of the lamppost is x. If you observe the positions of the lamppost and Anita, they are both standing vertical to the ground. Both form a right angle with the ground, in other words, are perpendicular to the ground. The rays of the sun passing through the lamppost and Anita make a common angle and also define the lengths of their shadows. As you can see, two triangles are formed. Now, are these triangles similar? In the two triangles, we have two pairs of corresponding angles equal. Hence, by the AA criterion of similarity, the triangles are similar. Recall that the sides of similar triangles are proportional. Taking the ratio of the sides, we get the equation 5 divided by 10 is equal to x divided by 30. On simplifying, we get x is equal to 5 multiplied by 30, the whole divided by 10, which is equal to 15. Therefore, the length of the lamppost is equal to 15 feet. Remember, when two triangles are similar, their corresponding angles are equal and their corresponding sides are proportional. But what about their areas? Will the areas be equal, or will they be proportional? To answer these questions, let's discuss the first theorem. The first theorem states that the ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. Consider triangle ABC and triangle PQR. It is given that these two triangles are similar. We will prove that the ratio of the areas of triangles ABC and PQR is equal to the square of the ratios of their corresponding sides AB, PQ, BC, QR, and CA, RP. To begin with, let's draw altitudes AM and PN on sides BC and QR respectively. Consider triangle ABC. Its area is equal to half the product of the base BC and the altitude AM. Similarly, the area of triangle PQR is equal to half the product of the base QR and the altitude PN. Now, let's take the ratios of the areas of the two triangles. On further simplification, the equation obtained is as shown here. Let's assign this as equation 1. This implies the ratio of the areas of triangle ABC and PQR is equal to the product of BC divided by QR and AM divided by PN. Now, let's consider the triangle ABM and triangle PQN. Angle B is equal to angle Q, as they are corresponding angles of similar triangles ABC and PQR. Angle AMB is equal to angle PNQ, as both angles measure 90 degrees. Thus, by the AA criterion, triangle AMB is similar to triangle PNQ. This also means that sides AM and PN are in the same ratio as sides AB and PQ. Let's assign this as equation 2. We know that triangle ABC and triangle PQR are similar. Therefore, we can say that their corresponding sides are in the same ratio. Let's assign this as equation 3. Now, recall equation 1. By applying equation 3, we can replace BC upon QR with AB upon PQ. Similarly, applying equation 2, we can also replace AM upon PN with AB upon PQ. Thus, we have proved that the ratio of the areas of triangles ABC and PQR is equal to the square of the ratio of sides AB and PQ. Please note, side AB and side PQ are corresponding sides of the similar triangles ABC and PQR. We can similarly prove for the other pair of corresponding sides BC, QR and CA, RP. Hence, we have proved the theorem, which states that the ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. Now, let's look at another important theorem, which states that if a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then the triangles on both sides of the perpendicular are similar to the whole triangle and to each other. Consider a right triangle ABC. It is given that angle B is the right angle and BD is perpendicular to the hypotenuse AC. Here, we will prove that triangle ABC, triangle ADB, and triangle BDC are similar. In triangles ADB and ABC, angle A is common. Similarly, angle ADB is equal to angle ABC as both are 90 degrees. Therefore, by the AA criterion of similarity, triangles ADB and ABC are similar. Let's assign this as observation 1. Similarly, we can prove that triangle BDC is similar to triangle ABC. Let's assign this as observation 2. From observations 1 and 2, we can conclude that triangle ADB is similar to triangle BDC. This also implies that the two triangles ADB and BDC are similar to triangle ABC. Thus, we've proved the theorem, which states that if a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then the triangles on both sides of the perpendicular are similar to the whole triangle and to each other. Next, we'll apply this theorem to prove another theorem, the Pythagoras theorem. Let's recall the Pythagoras theorem. It states that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Triangle PQR with the angle PQR equal to 90 degrees is given. We need to prove that the square of the hypotenuse PR is equal to the sum of the squares of the other two sides PQ and QR. Now, let's draw a perpendicular from the vertex Q to PR. Name it QS. The perpendicular QS divides the side PR into PS and SR. We now have two triangles, RSQ and PSQ. Consider the triangles PQR and PSQ. Here we can see that the angle P is common to both triangles. Thus, angle QPR is equal to angle SPQ. Similarly, angle PQR is equal to angle PSQ, as both the angles are equal to 90 degrees. By the AA criterion of similarity, we know that if two angles of one triangle are equal to two angles of another triangle, then the two triangles are similar. Hence, the triangle PQR is similar to triangle PSQ. Since the two triangles are similar, corresponding sides are proportional. Hence, side PQ divided by PS is equal to side PR divided by PQ. By simplification, we get PQ square is equal to PR multiplied by PS. Let's assign this as 1. Now, looking at triangles PQR and QSR, we can see that angle QRP is equal to angle QRS. Also, angle PQR and angle QSR are equal to 90 degrees. Again, by the AA similarity criterion, we know that triangle PQR is similar to triangle QSR. So we know that the corresponding sides are proportional. On simplification, we get QR square is equal to PR multiplied by SR. Let's assign this as observation 2. Now, adding the equations 1 and 2, we get PQ square plus QR square is equal to the product of PR and PS plus the product of PR and SR. From the figure we get PS plus SR is equal to PR. Hence we get PR square is equal to PQ square plus QR square. In other words, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Thus, the Pythagoras theorem is proved. Now, let's prove the converse of the Pythagoras theorem. The theorem states that if the square of one side is equal to the sum of the squares of the other two sides, then the angle opposite to the first side is a right angle. We have a triangle ABC in which AC square is equal to AB square plus BC square. We need to prove that angle B is equal to 90 degrees. Let's construct a right triangle PQR with a right angle at Q such that PQ is equal to AB and QR is equal to BC. By the Pythagoras theorem, in triangle PQR, PR square is equal to PQ square plus QR square. This is because angle Q is equal to 90 degrees. By construction, we know that the corresponding sides of triangles ABC and PQR are equal. Thus, PR square is also equal to AB square plus BC square. Let's assign this as observation 1. We know that AC square is equal to AB square plus BC square. Let's assign this as observation 2. From observations 1 and 2, we get AC is equal to PR. Let's assign this as observation 3. Now, in triangle ABC and PQR, AB is equal to PQ and BC is equal to QR by construction, and AC is equal to PR from observation 3. Therefore, by the SSS criterion for congruence, triangle ABC is congruent to PQR. Angle B is equal to angle Q by the corresponding parts of congruent triangles, and the angles Q and B are equal to 90 degrees by construction. Thus, the theorem is proved. You have reached the end of this section. Before moving to the next section, let's review the key points covered. The ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. If a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then the triangles on both sides of the perpendicular are similar to the whole triangle and to each other. The Pythagoras theorem states that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. The converse of the Pythagoras theorem states that in a triangle, if the square of one side is equal to the sum of the squares of the other two sides, then the angle opposite to the first side is a right angle. Hope you enjoyed this learning experience. We often see electric poles set up at regular intervals alongside roads. To determine the length of the cable between two electric poles, you measure the space or the distance between them. Consider a situation where you need to determine the length of cable required to lay electric lines between multiple points in a locality. If you create a map of the locality and transpose it onto a graph, you can derive the formula to calculate the distance between any 2 points in the locality. Welcome to the lesson, Distance Formula. In this lesson, you will learn how to apply the distance formula in coordinate geometry. At the end of this lesson, you will be able to apply the formula for calculating the distance between 2 points, Examine the corollaries of the distance formula. Consider the locality shown in the map. A power station is positioned centrally in the locality. The power station is laying cables to supply power to a new school and a stadium. The cable lines will go to the school via the stadium. The electricity department charges customers on the basis of the length of the cable required at the rate of 10,000 rupees per kilometer. Determine the expenses incurred by the school authorities for laying the cable. To determine the length of the cable required, we need to find the distance between the power station and the stadium, and then the distance between the stadium and the school. If the map is transposed onto a graph, you can derive the formula to find these distances through coordinates of various points. We can take the power station as the origin in the graph, as it is centrally located. First, let us derive a generic formula to obtain the distance between any two points with the help of their coordinates. In the graphical representation of the distance formula on the screen, let point P, x1, y1 represent the stadium on the graph, and point Q, x2, y2 represent the school. To find the distance between points P and Q, we draw a perpendicular line from point P to the x-axis. This line intersects the x-axis at point R. We draw another perpendicular line from point Q to the x-axis. This line intersects the x-axis at point S. The x-coordinate of P is x1. This denotes that the distance from origin O to point R on the x-axis is x1. Similarly, the x-coordinate of Q is x2. This denotes that the distance from origin O to point S on the x-axis is x2. Now, the length of RS can be determined. RS equals OS minus OR, which is x2 minus x1. Next, we draw a perpendicular line from point P to line QS intersecting at point T. If you notice, the distance from point P to R is y1, because the y-coordinate of P is y1, which is equal to ST. Similarly, distance from Q to S is y2. Therefore, distance TQ equals SQ minus ST equals y2 minus y1. Distance RS is equal to distance PT, which is equal to x2 minus x1. As you can see, PTQ is a right-angled triangle. Pythagoras' theorem states that in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Therefore, in triangle PTQ, the square of PQ is equal to the sum of the squares of PT and TQ. On substituting the values of PT and TQ, you get PQ equals square root of x2 minus x1 whole squared plus y2 minus y1 whole squared. Therefore, the distance between any two given points on a graph can be calculated using the formula square root of x2 minus x1 whole squared plus y2 minus y1 whole squared. Let us refer to the graphical map that shows the power station, the school, and the stadium. Since the cable has already been laid from the power station to the stadium, the power station will lay the cable from the stadium to the school. To calculate the length of the cable, we will calculate the distance between the stadium and the school. In the graph, the coordinate of the stadium is 3, 4, and the coordinate of the school is 6, 8. According to the given data, the cable costs 10,000 rupees per kilometer. Stadium P is at 3, 4, and school Q is at 6,8. The distance between the stadium and the school is represented by line segment PQ. The formula for calculating the distance is square root of x2 minus x1 whole squared plus y2 minus y1 whole squared. Substituting x1, y1 equals 3, 4 and x2, y2 equals 6, 8 and simplifying, you get distance PQ as 5 kilometers. Therefore, the total expenditure incurred by the school authorities for the cable will be 50,000 rupees. Using the same method, we can find the distance between any two points in the given locality. For instance, consider the length of the cable laid from the power station to an auditorium as shown on the map. On the graph, the power station is at the origin 0, 0 and the auditorium at -9, -12. The formula for calculating the distance is square root of x2 minus x1 whole squared plus y2 minus y1 whole squared. When you substitute x1, y1 equals 0, 0 and x2, y2 equals -9, -12 in the formula and simplify, you get the distance of OA as 15 kilometers. Thus, the distance between the power station and the auditorium is 15 kilometers. Thus, you can find the distance of any two points using the distance formula when the coordinates are given. The distance formula can be further simplified for specific scenarios. For instance, to find the distance of a point from the origin, that is, the center of your graph, you can use the following formula, square root of x squared plus y squared. To verify this, let us consider again the problem where we calculated the length of the cable laid from the power station to the auditorium. On the graph, the power station is placed at the origin 0, 0 and the auditorium at -9, -12. On applying the formula square root of x squared plus y squared, you get length OA is equal to 15 kilometers. As you can see, the values obtained using both the formulas are equal. So far you have been calculating distances between two points. However, there may be cases where we have three collinear points on a graph. According to a corollary of the distance formula, where 3 points on a graph are given, and the sum of the distances of 2 points from a third point is equal to the distance between the first 2 points. The 3 points on the graph are collinear. For example, in the given figure, the 3 points A, B and C are collinear if the sum of the distances between A and B and C is equal to the distance between A and C. In other words, the 3 points A, B and C are collinear if AB plus BC equals AC. Consider the distances between the power station at origin O, 0, 0, the stadium P, 3, 4 and the school Q, 6, 8. Apply the distance formula for the points given. You can calculate OP, PQ and OQ. Thus, OP is equal to 5 kilometers, PQ is equal to 5 kilometers, and OQ is equal to 10 kilometers. As you can see, the sum of OP and PQ is equal to OQ, and the power station, the stadium and the school all lie on the same line. That is, they are collinear. The electricity board is setting up an electric tower between two villages. The ratio of the distance between the tower and the two villages is 2:1. If we plot the villages and the tower on the graph, can we find the exact location of the tower? In this lesson, you will learn about the section formula. At the end of this lesson, you will be able to derive the section formula, apply the section formula to find a point that divides a line segment in the given ratio, and identify the corollaries of the section formula. Given the two endpoints of a line segment, you can determine the coordinates of the point that divide the line segment in the given ratio using the section formula. Let AB be a line segment. The coordinates of the points A and B be x1, y1 and x2, y2 respectively. Let the point P x, y divide the line segment in the ratio m:/n. Now, let's see how we can derive the formula to find the coordinates of point P. We need to find the x and y coordinates of point P using the values of m and n and the coordinates of point A and B. First, we draw perpendiculars from points A, P and B on the x-axis. The points where these perpendiculars intersect the x-axis are named Q, R and S respectively. Then we draw AC perpendicular to PR and PD perpendicular to BS. Two triangles ACP and PDB are created. You will observe that angle ACP is equal to angle PDB, that is 90 degrees. Angle PAC is equal to angle BPD. Based on the angle AA similarity criterion, we can conclude that triangle ACP is similar to triangle PDB. Since one of the angles is 90 degrees, they are similar right-angle triangles. In similar triangles, the ratio of the corresponding sides are equal. This leads us to equation 1. AP divided by PB is equal to AC divided by PD is equal to PC divided by BD. As you can see from the graph, AC equals QR. QR is equal to OR minus OQ is equal to X minus X1. Thus, AC is equal to QR is equal to OR minus OQ is equal to X minus X1. Similarly, PD is equal to RS. Thus, PD is equal to RS is equal to OS minus OR is equal to X2 minus X. Now let's move on to determine the heights of both the right-angle triangles. PC is equal to PR minus CR is equal to Y minus Y1. Similarly, BD is equal to BS minus DS is equal to Y2 minus Y. Earlier, from equation 1, we get AP divided by PB is equal to AC divided by PD. Substituting the values of AP, PB, AC and PD in the ratio of the corresponding sides, you get m divided by n is equal to x minus x1 divided by x2 minus x. Rearranging the expression, you get x multiplied by m plus n is equal to mx2 plus nx1. Simplifying the expression, you get x is equal to mx2 plus nx1 divided by m plus n. Similarly, you can substitute the values for sides PC and BD. From equation 1, AP divided by PB is equal to PC divided by BD. Rearranging the expression, you get y multiplied by m plus n is equal to my2 plus ny1. On simplifying, you get y is equal to my2 plus ny1 divided by m plus n. Thus, the coordinates of point P can be calculated using the formula obtained. mx2 plus nx1 divided by m plus n and my2 plus ny1 divided by m plus n. This formula is called the section formula. According to the section formula, any point P, x, y dividing a line segment in the ratio m:/n can be represented as mx2 plus nx1 divided by m plus n and my2 plus ny1 divided by m plus n. By applying the section formula obtained, you can now determine the exact location of the electric tower. Let's review the problem again. The village A is located at 2, -1 and village B at 5, 2. The distance of the tower from village A is twice the distance of the tower from village B. If the map of this region is transposed onto a graph, find the exact location of the tower. According to the problem, coordinates of village A, x1, y1 is equal to 2, -1. Coordinates of village B, x2, y2 is equal to 5, 2. The ratio of the distances of the tower from villages A and B, or m:/n equals 2:1. Substituting the coordinates of A, B, and the ratio m:/n in the section formula, you can determine the coordinates to specify the position of the tower. Simplifying, you get the coordinates of P as 4, 1. The electric tower is located between villages A and B at 4, 1. Some corollaries to the section formula can be derived for some specific cases. According to the first corollary, where the ratio of sections of a line segment m:/n equals 1:1, the point is the midpoint of the line segment. In such a case, the midpoint of a line segment joining x1, y1 and x2, y2 is x1 plus x2 divided by 2, y1 plus y2 divided by 2. The second corollary relates to the coordinates of the centroid of a triangle. The centroid of a triangle is the point of intersection of its medians. The centroid of a triangle divides the medians in the ratio 2:1. Thus, based on the section formula, centroid G of a triangle with vertices x1, y1, x2, y2 and x3, y3 is x1 plus x2 plus x3 divided by 3, y1 plus y2 plus y3 divided by 3. Welcome to the lesson on area of a triangle. At the end of this lesson, you will be able to derive the formula for the area of a triangle for which the vertices are given on a Cartesian plane and apply the formula to calculate the area of a triangle. Here are two triangles, triangle ABC and triangle PQR. Consider the triangle ABC. The length of the base AB and the corresponding height CD are given. Next, consider the triangle PQR. Here the length of the sides PQ, QR and PR are given. How will you find the areas of these two triangles? We can calculate the area of triangle ABC by applying the formula half the product of the base and its corresponding height. To calculate the area of the triangle PQR, we can apply Heron's formula. This formula uses the semi-perimeter and the lengths of the sides of the triangle to calculate the area. Now look at this triangle. Oh, where is the triangle? All we can see here are 3 points, A, B, and C. Let's join the points A, B, and C. Here's our triangle ABC. Now, how do we calculate the area of this triangle? There is a method to calculate the area of any triangle when the vertices are given as points in a Cartesian plane. Let's derive a formula that will help us calculate the area of the triangle in terms of the coordinates of vertices A, B, and C. Let's see how. The coordinates of point A are x1, y1. Point B are x2, y2. And point C are x3, y3. Let's derive a formula to calculate the area using these coordinates. Draw perpendiculars from the points A, B, and C onto the x-axis. Mark the points where the perpendiculars meet the x-axis as L, M, and N, respectively. 3 quadrilaterals ABML, ALNC, and BMNC are formed. Now, let's observe the complete figure. Here, if we remove the area of quadrilateral BMNC from the sum of the areas of quadrilaterals ABML and ALNC, we get the area of the triangle ABC. Let's first calculate the areas of the quadrilaterals. In all 3 quadrilaterals, ABML, ALNC, and BMNC, a pair of sides are parallel. In the quadrilateral ABML, BM and AL are parallel. In the quadrilateral ALNC, AL and CN are parallel. And in the quadrilateral BMNC, BM and CN are parallel. All 3 quadrilaterals are trapeziums. Therefore, our equation changes as shown. The area of a trapezium is given by half the product of sum of parallel sides and the distance between the parallel sides. In the quadrilateral ABML, the side BM is y2, AL is y1. The distance between BM and AL is ML, that is x1 minus x2. Therefore, the area of trapezium ABML is half multiplied by y1 plus y2 multiplied by x1 minus x2. Similarly, the area of the trapezium quadrilaterals ALNC is half multiplied by y1 plus y3 multiplied by x3 minus x1. Similarly, for the area of trapezium BMNC is half multiplied by y2 plus y3 multiplied by x3 minus x2. To obtain the area of the triangle ABC, add the areas of trapeziums ABML and ALNC and subtract the area of trapezium BMNC. We will get the following expression. Let's further simplify this expression. Expanding the expression and then cancelling the like terms, we get the following expression for the area of the triangle. Therefore, this expression can be used to calculate the area of the triangle given its vertices as coordinates. An important point to note here is that if the area of the triangle obtained is 0, then the 3 points are collinear. You have reached the end of this section. Before moving on to the next section, let's recap the key points covered. The area of a triangle of which the vertices are given as points in a Cartesian plane can be calculated by the following formula. An important point to note here is that if the area of the triangle obtained is 0, then the 3 points are collinear. Hope you enjoyed your learning experience. Welcome to the lesson on trigonometric ratios. At the end of this lesson, you will be able to state the trigonometric ratios of an acute angle in a right-angled triangle. You will also be able to calculate the trigonometric ratios of an acute angle using Pythagoras' theorem. Here's Jack. He has been given a unique problem in his math activity class. He has to find the height of the clock tower in the campus of his school. Tough job. Actually, there is a branch of mathematics called trigonometry, which can be applied to solve Jack's problem. The word trigonometry is derived from ancient Greek words, which mean study of triangles. Trigonometry is the study of how the sides and angles of a triangle are related to each other. In this lesson, we will study the ratios of the sides of a right triangle with respect to its acute angles. Let's begin by reviewing some key terms related to right-angled triangles. You may already know some of these. Triangle ABC is a right-angled triangle. A right-angled triangle is also called a right triangle. In this triangle, angle ABC is a right angle, as it measures 90 degrees. Angle BAC and angle ACB are acute angles, as they measure less than 90 degrees. Please note that angles can also be named by the vertex when they are formed. For example, angle BAC can be referred to as angle A, angle CBA as angle B, and angle ACB as angle C. The longest side of the triangle is side AC, which is opposite to the right angle. This side is called the hypotenuse. Now, consider angle A. Side BC lies opposite to angle A. Let's call it the side opposite to angle A. Side AB lies next to angle A. It is said to be a side adjacent to angle A. Similarly, let's consider angle C. Side AB is the side opposite to angle C, while side BC is a side adjacent to angle C. Note that the terms opposite and adjacent change based on the angle being considered. The hypotenuse, however, remains the same. Now, let's come back to Jack. We'll move Jack to a position such that a line can be drawn joining the top of the clock tower and Jack's head. Oh, looks like the top of the tree also falls on the same line. Let's drop perpendiculars from this line to the ground passing through the clock tower, the tree, and Jack. We now have three right triangles: triangle PQC, triangle ABC, and triangle MNC. Angle C is common to all the three triangles. Each triangle has one angle, which is a right angle. It means that two pairs of corresponding angles of the three triangles are equal. Thus, by the angle sum property, the third pair of angles of these three triangles is also equal. This means that the triangles PQC, ABC, and MNC are similar to each other by the AA similarity criterion. Now, what can we say about the corresponding sides of these triangles? Recall that in case of similar triangles, the three pairs of corresponding sides are proportional. This means that the ratios PQ upon PC, AB upon AC, and MN upon MC are equal. Now, let's consider angle C in all the three triangles. In relation with angle C, sides PC, AC, and MC are all hypotenuses, and sides PQ, AB, and MN are all sides opposite to angle C. Thus, we can see that, with respect to angle C, the ratio of the opposite side and the hypotenuse for all the three triangles are constant. This constant ratio can be written as opposite side of angle C divided by hypotenuse. In trigonometry, this ratio is given a name. It is called the sine of angle C. The sine of angle C is written as sine C. Here, angle C is an acute angle. The sine of an acute angle in a right-angled triangle is defined as the ratio of the side opposite to the acute angle and the hypotenuse. Similarly, in relation with angle C, sides PC, AC, and MC are hypotenuses, and sides QC, BC, and NC are sides adjacent to angle C. The ratio of the adjacent sides and the hypotenuse is also constant. This constant ratio is named as the cosine of angle C. The cosine of angle C is written as cos C. The cosine or cos of an acute angle in a right-angled triangle is defined as the ratio of the side adjacent to the acute angle and the hypotenuse. Similarly, for triangles PQC, ABC, and MNC, the ratio of sides opposite to angle C and sides adjacent to angle C is constant. This constant ratio is named as the tangent of angle C. The tangent of angle C is written as tan C. The tangent or tan of an acute angle in a right-angled triangle is defined as the ratio between the side opposite to the acute angle and the side adjacent to the same acute angle. Let's recap the three trigonometric ratios that we just discussed. The table shows the trigonometric ratios for an acute angle of a right triangle. The measure of the acute angle is taken as theta. Now, here's an easy way to remember these trigonometric ratios. Look at the bold letters. They form a mnemonic. So, ka, to. It is pronounced so, ka, to, a. The so stands for sine of an angle is opposite side over hypotenuse. The ka stands for cosine of an angle is adjacent side over hypotenuse. The toa stands for tangent of an angle is opposite side over adjacent side. Memorize this to remember these ratios. Apart from the three primary trigonometric ratios, the reciprocals of these ratios are also defined. The cosecant or cosec of an acute angle in a right-angled triangle is the reciprocal of the sine of the angle. Thus, the cosecant of angle C or cosec C is equal to the ratio between the hypotenuse and the side opposite to angle C. Or, the cosecant of angle C is equal to AC upon AB. The secant or sec of an acute angle in a right-angled triangle is reciprocal of the cosine of the angle. Thus, the secant of angle C is equal to the ratio between the hypotenuse and the side adjacent to angle C. Or, the secant of angle C is equal to AC upon BC. The cotangent or cot of an acute angle in a right-angled triangle is reciprocal of the tangent of the angle. Thus, the cotangent of angle C is equal to the ratio between the side adjacent to angle C and the side opposite to angle C. Or, the cotangent of C is equal to BC upon AB. Here are all the 6 trigonometric ratios of an acute angle of a right triangle. The values of trigonometric ratios do not vary with the lengths of the sides if the angles remain the same. Thus, we can conclude that trigonometric ratios are only dependent on the ratio of the sides and not on the lengths of the sides. An important point to note is that when the square of these ratios is written as sine square c in place of sine c square, this applies for all trigonometric ratios. Let's try an example. Consider a right triangle ABC. Its two sides are 3 units and 4 units respectively, and its hypotenuse is 5 units. For angle C, the opposite side is AB, which is 3 units, and the adjacent side is BC, which is 4 units. Let's find the trigonometric ratios for angle C. Sine C will be equal to opposite side to angle C divided by hypotenuse, which is equal to 3 divided by 5. Cos C will be equal to adjacent side to angle C divided by hypotenuse, which is equal to 4 divided by 5. Tan C is equal to opposite side to angle C divided by adjacent side to angle C, which is equal to 3 divided by 4. Cosec C is reciprocal of sin C. Hence, it is equal to 5 divided by 3. Sec C is reciprocal of cos C. Hence, it is equal to 5 divided by 4. And cot C is reciprocal of tan C. Hence, it is equal to 4 divided by 3. Now, consider the other acute angle, angle A in the right-angled triangle ABC. Are the trigonometric ratios for angle A same as those of angle C? As you can see in the table, the trigonometric ratios of angles C and A are different since their adjacent and opposite sides are different. In case of the trigonometric ratios of an acute angle in a right-angled triangle, if any one of the ratios is known, all the other trigonometric ratios of the angle can be calculated. We'll apply this understanding to help Jack find the height of the clock tower. In triangle MNC, side MN, which represents Jack's height, is equal to 6 feet, and side NC is 8 feet. With reference to angle C, MN is the opposite side and NC is the adjacent side. Thus, tan C is equal to opposite side to angle C divided by adjacent side to angle C, which is equal to 6 divided by 8. On simplifying, we get 3 divided by 4. Now, the distance between point C and the base of the clock tower, which is represented by side QC, is 40 feet. In triangle PQC, side QC is the side adjacent to angle C. Let's assume the height of the tower, which is represented by side PQ, as x. Tan C is equal to PQ divided by QC, which is equal to x divided by 40. We know that tan C is constant. Thus, ratio of PQ and QC is equal to ratio of MN and NC. Substituting the values, we get x upon 40 is equal to 3 upon 4. On simplifying, we get the value of x as 30 feet. Therefore, the height of the clock tower is 30 feet. Let's solve some more examples. Here, one trigonometric ratio is given. We will use this ratio to find the other trigonometric ratios. Consider angle C in the given figure. It is given that cos C is equal to 4 by 5. Now, cos C is equal to the ratio between its adjacent side BC and hypotenuse AC. Thus, we can say that AC is equal to 5x and BC is equal to 4x, where x is some constant. The reason we include a constant x here is that the trigonometric ratio just gives us the proportions of two sides, not their exact values. In both these triangles, cos C is 4 by 5, though the actual lengths of their sides are different. Now, using Pythagoras' theorem, we can find the length AB. Putting in the values and simplifying, we find AB is equal to 3x. Since we know the values of all the three sides of triangle ABC, we can calculate all other trigonometric ratios. For example, sin C is equal to 3x upon 5x, or 3 by 5. Similarly, tan C is equal to 3x upon 4x, or 3 by 4. Let us take another example. Suppose in the given right-angled triangle ABC, sin A is equal to 2 by 3. Now, sin A is equal to the ratio between its opposite side BC and hypotenuse AC. Thus, we can say that AC is equal to 3x and BC is equal to 2x, where x is some constant. Again, using Pythagoras' theorem, we can find the length AB. Putting in the values and solving, we find AB is equal to root 5x. Now, since we know the values of all three sides of triangle ABC, we can calculate all other trigonometric ratios. For example, cosine of angle A is equal to root 5x upon 3x, or root 5 by 3. Similarly, tangent of angle A is equal to 2x upon root 5x, or 2 by root 5. This brings us to the end of our discussion on trigonometric ratios. Memorize these ratios by heart and try finding these ratios in different right-angled triangles. Welcome to the lesson on trigonometric ratios of specific angles. At the end of this lesson, you will be able to state the trigonometric ratios of angles of measure 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. You will also be able to state trigonometric ratios of complementary angles. Consider angle C in the right-angled triangle ABC. You already know that angle C has some trigonometric ratios associated with it. We are now going to see some special situations with respect to the values of the angle C. Now, let us see what happens if we decrease angle C till it approaches 0. Observe carefully. As angle C decreases, the length of AB decreases. At the same time, point A approaches point B, so that length AC approaches length BC. When angle C becomes 0, we can say that the length of AB, the side opposite to angle C, also becomes 0. Also, the length of hypotenuse AC becomes equal to the length of BC, the side adjacent to angle C. Let us calculate the trigonometric ratios of angle C in this position. We know that sin C is equal to the ratio between AB, the side opposite to angle C, and AC, the hypotenuse. We have seen that AB becomes 0 when angle C is equal to 0 degrees. 0 divided by any quantity is 0. Thus, we can say that sin 0 is equal to 0. We know that cos C is equal to the ratio between BC, the side adjacent to angle C, and AC, the hypotenuse. We have seen that AC becomes equal to BC when angle C is equal to 0 degrees. Thus we can say that cos 0 is equal to 1. We know that tan theta is equal to sin theta divided by cos theta. Substituting theta equal to 0 degrees and simplifying, we get tan 0 degrees is 0. Let us look at other trigonometric ratios of 0 degrees. Cosec 0 is equal to reciprocal of sin 0, which is 0. Since any quantity divided by 0 is undefined, cosec 0 is undefined. Sec 0 is equal to reciprocal of cos 0. Thus, sec 0 is equal to 1. Cot 0 is equal to reciprocal of tan 0. Therefore, cot 0 is undefined. Let us quickly recap the trigonometric ratios of an angle that measures 0 degrees. Consider angle C in the right-angled triangle ABC. Now, let us see what happens if we move angle C till it approaches angle B, which is equal to 90 degrees. Observe carefully. As angle C increases, the length of BC decreases. At the same time, point C approaches point B, so that the length AC approaches the length AB. When angle C becomes 90 degrees, we can say that the length of BC, the side adjacent to angle C, also becomes 0. Also, the length of the hypotenuse AC becomes equal to the length of AB, the side opposite to angle C. Let us calculate the trigonometric ratios of angle C in this position. We know that sin C is equal to the ratio between AB, the side opposite to angle C, and AC, the hypotenuse. We have seen that AC becomes equal to AB when angle C is equal to 90 degrees. Thus, we can say that sine 90 is equal to 1. We know cos C is equal to the ratio between BC, the side adjacent to angle C, and AC, the hypotenuse. We have seen that BC becomes 0 when angle C is equal to 90 degrees. 0 divided by any quantity is 0. Thus we can say that cos 90 is equal to 0. We know that tan theta is equal to sine theta divided by cos theta. Substituting theta equal to 90 degrees and simplifying, we get tan 90 degrees is undefined. Let us move on to other trigonometric ratios of 90 degrees. Cosec 90 is equal to reciprocal of sine 90, which is 1. Thus, cosec 90 is equal to 1. Sec 90 is equal to reciprocal of cos 90, which is 0. Thus, sec 90 is undefined. Cot 90 is equal to the ratio of cos 90 and sine 90. Hence, cot 90 becomes 0 upon 1, which is equal to 0. Thus, cot 90 is equal to 0. As tan 90 degrees is undefined, we do not consider the definition that cot of an angle is the reciprocal of tan of the angle. Let us quickly recap the trigonometric ratios of a 90-degree angle. Consider a right-angled triangle ABC in which angle C is equal to 45 degrees. Now, this has some interesting effects on triangle ABC. Given angle C equal to 45 degrees and angle B equal to 90 degrees, by angle sum property, we find that angle A is also equal to 45 degrees. Since sides opposite to equal angles in a triangle are equal, we can say that the length of AB is equal to the length of BC. Let this length be x. Applying Pythagoras' theorem in triangle ABC, we find the length of hypotenuse AC as root 2 times x. Now, we are all set to find trigonometric ratios of the 45-degree angle C. Sine 45 degrees is equal to the ratio of AB, the side opposite to the angle C, and the hypotenuse AC. Putting in the values of AB and AC, we get sine 45 degrees as 1 by root 2. Cos 45 degrees is equal to the ratio of BC, the side adjacent to the angle C, and the hypotenuse AC. Putting in the values of BC and AC, we get cos 45 degrees as 1 by root 2. Now, tan 45 degrees is equal to the ratio between sine 45 degrees and cos 45 degrees. Since sin 45 and cos 45 are both equal to 1 by root 2, tan 45 is equal to 1. Cosec 45 is equal to the reciprocal of sin 45 degrees. Thus, cosec 45 is equal to root 2. Sec 45 degrees is equal to the reciprocal of cos 45 degrees. Thus, sec 45 degrees is equal to root 2. Note that sin 45 degrees is equal to cos 45 degrees and cosec 45 degrees is equal to sec 45 degrees. Cot 45 degrees is equal to the reciprocal of tan 45 degrees. Since tan 45 degrees is equal to 1, cot 45 degrees is also equal to 1. Let us quickly recap the trigonometric ratios of 45-degree angle. Consider an equilateral triangle ABC. By definition, each angle of an equilateral triangle is equal to 60 degrees and all its sides are equal. Let the length of each side of equilateral triangle ABC be x. Let us draw a perpendicular AD from vertex A to its opposite side BC. Again, by definition, a perpendicular drawn from a vertex to its opposite side in an equilateral triangle bisects the angle at the vertex and its opposite side. Thus, AD divides angle A into two equal parts. It also divides side BC into two equal parts, BD and CD, each equal to x by 2. Applying Pythagoras' theorem to triangle ADB, we get the length of side AD as root 3 by 2 times x. Now, let us find trigonometric ratios of angle B equal to 60 degrees in triangle ADB. Sin 60 degrees is equal to the ratio of AD, the side opposite to the angle B, and the hypotenuse AB. Putting in the values of AD and AB, we get sin 60 degrees as root 3 by 2. Cos 60 degrees is equal to the ratio of BD, the side adjacent to the angle B, and the hypotenuse AB. Putting in the values of BD and AB, we get cos 60 degrees as 1 by 2. Tan 60 degrees is equal to the ratio between sin 60 degrees and cos 60 degrees. Putting in the values of sin 60 degrees and cos 60 degrees, we get tan 60 degrees is equal to root 3. Cosec 60 degrees is equal to the reciprocal of sin 60 degrees. Thus, cosec 60 degrees is equal to 2 by root 3. Sec 60 degrees is equal to the reciprocal of cos 60 degrees. Thus, sec 60 degrees is equal to 2. Cot 60 degrees is equal to the reciprocal of tan 60 degrees. Since tan 60 degrees is equal to root 3, cot 60 degrees is equal to 1 by root 3. Let us quickly recap the trigonometric ratios of a 60-degree angle. Remember, when we drew AD perpendicular to BC, we not only divided BC into two equal parts, but we also divided angle BAC into two equal parts. Now, let us find trigonometric ratios of angle BAD equal to 30 degrees in triangle ADB. Sin 30 degrees is equal to the ratio of BD, the side opposite to the angle BAD, and the hypotenuse AB. Putting in the values of BD and AB, we get sin 30 degrees as 1 by 2. Cos 30 degrees is equal to the ratio of AD, the side adjacent to the angle BAD, and the hypotenuse AB. Putting in the values of BD and AB, we get cos 30 degrees as root 3 by 2. Tan 30 degrees is equal to the ratio between sin 30 degrees and cos 30 degrees. Putting in the values of sin 30 degrees and cos 30 degrees, we get tan 30 degrees is equal to 1 by root 3. Cosec 30 degrees is equal to the reciprocal of sin 30 degrees. Thus, cosec 30 degrees is equal to 2. Sec 30 degrees is equal to the reciprocal of cos 30 degrees. Thus, sec 30 degrees is equal to 2 by root 3. Cot 30 degrees is equal to the reciprocal of tan 30 degrees. Since tan 30 degrees is equal to 1 by root 3, cot 30 degrees is equal to root 3. Let us quickly recap the trigonometric ratios of a 30-degree angle. Consider the two acute angles, angle A and angle C, in a right-angled triangle, ABC. By the angle sum property of triangles, we know that the sum of angles A, B and C in the triangle ABC is 180 degrees. Angle B in the given triangle is a right angle. Putting in the value of angle B in the previous equation and simplifying, we see that the sum of angles A and C is equal to 90 degrees. Thus, we can say that angles A and C are complementary angles. What is true for triangle ABC is true for all right-angled triangles. The two angles, besides the right angle in a right-angled triangle, are always acute angles and complementary angles. Now, we can also represent angle C as 90 degrees minus angle A. The table here shows the trigonometric ratios of angle A. The table here shows the trigonometric ratios of complementary angle of angle A, that is, angle C, or 90 degrees minus A. Now, let us compare the values of the trigonometric ratios of the two complementary angles. Comparing the two tables, we see that the value of sin 90 minus A, that is, AB upon AC, is also equal to cos A. Similarly, we see that the value of cos 90 minus A, that is BC upon AC, is also equal to sin A. Similarly, we can find relationships between the other trigonometric ratios of angle A and its complementary angle. The table here summarizes the relationships between trigonometric ratios of complementary angles. Welcome to the lesson on trigonometric identities. At the end of this lesson, you will be able to state 3 basic trigonometric identities. You will also be able to apply these trigonometric identities to solve problems. Here is a triangle ABC. By the angle sum property of triangles, we know that the angle A plus angle B plus angle C is 180 degrees. This equation is true in all triangles. An equation that is true for all values of the quantities that it contains is called an identity. Since the equation angle A plus angle B plus angle C is equal to 180 degrees is true for all triangles, this equation is an identity. Consider the right-angled triangle PQR. By Pythagoras' theorem, we know that in the right-angled triangle PQR, the sum of the square of the sides PQ and QR is equal to the square of the hypotenuse PR. Now, let us derive some trigonometric identities by dividing both sides of equation 1 by the squares of different sides of triangle PQR. Let us start with the hypotenuse PR. Let us divide both sides of equation 1 by PR square. Since the numerator and the denominator are the same, the right-hand side of the equation becomes 1, and we get equation 2. If angle R in triangle PQR is equal to theta, then the ratio PQ upon PR is equal to sin theta, and the ratio QR upon PR is equal to cos theta. Putting the values of these ratios in equation 2, we get an equation sin square theta plus cos square theta is equal to 1. This equation is a trigonometric identity. This trigonometric identity is true for all values of angle theta from 0 degrees to 90 degrees. Now, consider side PQ, the opposite side for angle theta. Let us divide both sides of equation 1 by PQ square to get equation 3. Now, in triangle PQR, the ratio QR upon PQ is equal to cot theta, and the ratio PR upon PQ is equal to cosec theta. Putting the values of these ratios in equation 3, we get an equation 1 plus cot square theta is equal to cosec square theta. This equation is a trigonometric identity. From the trigonometric ratios of specific angles, we know that cot 0 and cosec 0 are not defined. Thus, This identity is true for all values of angle theta greater than 0 degrees and less than or equal to 90 degrees. Now, consider side QR, the adjacent side for angle theta. Let us divide both sides of equation 1 by QR square to get equation 4. Now, in triangle PQR, the ratio PQ upon QR is equal to tan theta, and the ratio PR upon QR is equal to sec theta. Putting the values of these ratios in equation 4, we get an equation 1 plus tan square theta is equal to sec square theta. This equation is a trigonometric identity. From trigonometric ratios of specific angles, we know that tan 90 and sec 90 are not defined. Thus, this identity is true for all values of angle theta greater than or equal to 0 degrees and less than 90 degrees. Welcome to the lesson on heights and distances. At the end of this lesson, you will be able to define the angle of elevation and the angle of depression. Can we determine the heights and distances of distant objects that cannot be measured directly? For example, the distance of an island from the ship, or the height of a lighthouse that is at a certain distance from a ship, or the height of a mountain, and the speed of a moving object. Yes, if we know some suitable angles and distances, we can apply trigonometry to find the required heights and distances. Let's learn more about this. We'll begin with a simple example. Here, a wildlife photographer is clicking photographs of seagulls. This particular seagull flying overhead has caught the photographer's fancy. Oh, it seems the seagull has spotted a prey. The seagull has suddenly changed its path of flight. Let's trace the path of the camera's view. Two lines are formed. These lines are called the line of sight. In the first instance, the seagull was flying overhead, and the camera was elevated upwards with respect to the horizontal line. While in the second instance, the camera was bent downwards with respect to the horizontal line. The angle which is formed by the line of sight, which is above the line of the observer's eye, is called the angle of elevation. And the angle formed by the line of sight, which is below the line of the observer's eye, is called the angle of depression. Now, let's consider another example. A jet plane is flying at an angle of 60 degrees from a point on ground level, which is horizontal line. After a flight of 15 seconds, the angle at which the plane is flying changes to 30 degrees. The jet plane is flying at a constant height of 1,800 meters. Given this information, can we find the speed of the jet plane? First, we'll draw a rough figure based on the problem. Here, A is the point of observation and AC is the horizontal line through the point of observation. P is the point at which the height of the plane is first observed, and Q is the position of the plane after 15 seconds. AP and AQ are the two lines of sight. PB and QC are the perpendicular distances of point P and Q respectively from the horizontal line AC. The angle PAB is the first angle of elevation, which is equal to 60 degrees, and the angle QAC is the second angle of elevation, which is equal to 30 degrees. PB is equal to 1,800 meters, which is the constant height of the jet plane. Let's assume that the speed of the jet plane is x meters per second. In triangle ABP, angle PAB, which is equal to 60 degrees. Applying trigonometry, we know that tan theta is equal to the opposite side to theta divided by the adjacent side to theta. Therefore, in triangle ABP, tan 60 degrees is equal to PB divided by AB. Recall that tan 60 degrees is equal to the square root of 3 and given PB is equal to 1,800. Substituting these values and simplifying, we get AB is equal to 600 root 3 meters. Similarly, in triangle ACQ, the angle QAC is equal to 30 degrees. We know that tan 30 degrees is equal to opposite side to 30 degrees divided by adjacent side to 30 degrees, that is QC upon AC. Let's substitute tan 30 degrees as 1 upon square root of 3 and QC as 1,800, since QC and PB are equal as the jet plane is moving at a constant height. On simplifying, we get AC is equal to 1800 root 3 meters. From the figure, BC is equal to AC minus AB. Substituting the values of AC and AB and simplifying, we get BC is equal to 1200 root 3 meters. This is the distance travelled by the jet plane in 15 seconds. Recall that the speed is equal to the distance travelled divided by time taken. On substituting the corresponding values of distance and time in this formula, we get the speed as 1200 root 3 upon by 15. On further calculation, we get the speed as 138.56 meters per second. Therefore, the speed of the jet plane is 138.56 meters per second. You have reached the end of this section. Before moving on to the next section, let's recap the key points covered. Line of sight. The line joining the observer's eye and the object observed. Angle of elevation. The angle between the horizontal line and the line of sight which is above the observer's eye. Angle of depression. The angle between the horizontal line and the line of sight which is below the observer's eye. Hope you enjoyed your learning experience. Welcome to the lesson on tangents to a circle. At the end of this lesson, you will be able to define a tangent to a circle and prove that a tangent to a circle is perpendicular to the radius of the circle drawn at the point of contact. You will also be able to prove that tangents drawn to a circle from an external point are equal in length. Have you ever noticed the wheels of a vehicle moving on the road? What does the surface of the road look like against the wheel? Does it look like a line touching a circle at one point? Well, this is what you call a tangent. Here are a few more lines. Are all these tangents to the given circle? Let's find out. Observe this line. Note that this line does not touch the circle at any point. Thus, it is not a tangent to the circle. Now, what about this line? This line touches the circle at 2 points. This line isn't a tangent to the circle either. A line that touches a circle at 2 points is called a secant of the circle. Observe these lines. Each of these lines touches the circle at only 1 point. A line that touches a circle at only 1 point is called a tangent to the circle. The point where a tangent touches a circle is called its point of contact. Here P is the point of contact of tangent AB with the circle, and Q is the point of contact of the tangent AC with the circle. Here is a circle with a point P marked on it. How many tangents can you draw to the circle at the given point P? We can draw an infinite number of lines passing through this point. But are all these lines drawn through the point P tangents to the given circle? As you can see, all these lines touch the circle at 2 points. They are secants, but not tangents to the given circle. Now observe this line. This is the only line that touches the circle only at 1 point. This implies we can draw only one tangent at any given point on a circle. Here are 3 friends, Mr. O, Mr. A, and Mr. B. While Mr. O is standing at the center of a circle, Mr. A and Mr. B are standing on a tangent to the circle at point P as shown. Mr. O thinks that if he walks straight to point P, he will meet Mr. A and Mr. B at right angles. Let's see if this is true. To verify Mr. O's claim, we have to verify the theorem that states that the tangent at any point on a circle is perpendicular to the radius drawn to its point of contact. Here we have a circle with the tangent AB drawn to it at point P. OP is the radius of the circle. Now, we have to prove that OP is perpendicular to AB. Now consider another point C, other than P on the tangent AB. Can point C lie on the given circle? Certainly not. Because if C lies inside the circle, then the line segment AB has 2 points of contact with the circle, which contradicts that a tangent has only 1 point of contact with the circle. Thus C must lie outside the circle. Now compare the length of OC and OP. Which do you think is longer? OC is definitely longer than OP, since point P lies on the circle and point C lies outside the circle. This is true for all points on the tangent AB. Since OC is longer than OP for any point C on AB, we can say that OP is the shortest distance between point O and the line segment AB. Now the shortest distance of a point from a line segment is the perpendicular distance of the point from the line segment. Thus OP is perpendicular to AB. Hence the theorem is proved. So Mr. O was right after all. Meet the great explorer, Mr. A. On his expedition, his path is blocked by a huge circular crater. Mr. A has to find a way to go past it. Now, being a man of great courage, he doesn't want to be too far from the danger, so he wants to go across a path that is at tangent to the crater. How many such paths are possible? Actually, there are just 2. As you can draw only 2 tangents to a circle from any point lying outside it. So Mr. A has the choice of going along either AB or AC. Which one should he take? Which route is the shortest? Let's find out. To help Mr. A make up his mind, let us prove the theorem that states tangents drawn to a circle from an external point are equal in length. Here we have 2 tangents AB and AC drawn from an external point A to points B and C on a circle. We have to prove that AB and AC are equal in length. Let us start by joining the external point A to the center of the circle O. Now join OB and OC. Here OB is perpendicular to AB, since the tangent at any point on a circle is perpendicular to the radius drawn to its point of contact. That is, angle OBA is equal to 90 degrees. Similarly, angle OCA is equal to 90 degrees. Now, in triangles OBA and OCA, angle OBA is equal to angle OCA, which is equal to 90 degrees. OB is equal to OC, since they are the radii of the same circle, and OA is a common side. Thus, triangles OBA and OCA are congruent by the RHS congruence rule. Since triangles OBA and OCA are congruent, AB is equal to AC, as corresponding sides of congruent triangles are equal. Hence, the theorem is proved. This also means that Mr. A can walk along either AB or AC. He will be covering the same distance. You have reached the end of this section. Before moving on to the next section, let's recap the key points covered. The tangent at any point on a circle is perpendicular to the radius drawn to its point of contact. Tangents drawn to a circle from an external point are equal in length. Hope you enjoyed your learning experience. Welcome to the lesson on constructions. At the end of this lesson, you will be able to divide a line segment in any given ratio. You will also be able to construct a triangle similar to a given triangle and draw tangents to a circle from an external point. Here are the geometrical instruments we will use to make the required constructions. You must be familiar with all of them. Let us begin. We'll start with the construction that divides a given line segment in a specific ratio. The given line segment is AB, and we'll divide it in the ratio 1:3. There are two ways of doing this. Using the first method, as step 1, draw a segment AC of any convenient length, making an acute angle with the given line segment AB. Now, you have to mark a few points at an equal distance from each other on AC. The number of points depends on the ratio in which you have to divide the given line segment. If the ratio is x:y, the number of points is x plus y. Here, the given ratio is 1:3, so the number of points you will mark on AC is 1 plus 3, which is equal to 4. Now, open the compass to any small convenient length. As step 2, mark 4 points: x1, x2, x3, and x4 on AC, so that AX1 is equal to x1 x2 is equal to x2 x3 is equal to x3 x4. Make sure that the distance to which the compass is open is not disturbed as you mark the points. As step 3, draw a line to join the points x4 and B. As step 4, use a pair of set squares to draw a line parallel to x4b from the point x1 to intersect the given line segment AB at point P. Point P divides the line segment AB in the ratio 1:3. Now, let us verify this construction mathematically. In the triangle ABX4, we know x1P is parallel to x4B. Thus, using the basic proportionality theorem, the ratio AX1 upon x1 x4 is equal to the ratio AP upon PB. By construction, AX1 upon X1X4 is equal to 1 upon 3. Thus, AP upon PB is also equal to 1 upon 3. In other words, the ratio AP is to PB is 1:3. Now, let us learn about the second method to divide a line segment in any given ratio. Using the second method, start by drawing a segment AC of a convenient length, making an acute angle with the given line segment AB. Let us make a mark at, say, the 30-degree point. Now, draw the line segment AC as shown. Now we have to draw a segment BD of any convenient length making the same angle with AB as AC. Let us again make a mark at the 30-degree point. Now draw the segment BD as shown. Next, mark a few points at an equal distance from each other on AC and BD. The number of points depends on the ratio in which you have to divide the given line segment. If the ratio is X is to Y, mark X number points on AC and Y number points on BD or vice versa. Here the given ratio is 1:3, so let us mark 1 point on AC and 3 points on BD. Now open the compass to a small convenient length. As step 3, mark 1 point, X1 on AC, and 3 points, Y1, Y2, and Y3 on BD, such that AX1 is equal to BY1 is equal to Y1 Y2 is equal to Y2 Y3. Make sure that the distance to which the compass is open is not disturbed as you mark the points. As step 4, draw a line to join the points X1 and Y3 to intersect AB at point P. Point P divides the line segment AB in the ratio 1:3. Now, let us verify this construction mathematically. Consider triangles APX1 and BPY3. In triangles APX1 and BPY3, angle PAX1 is equal to angle PBY3 by construction, since we made both the angles equal to 30 degrees. Further, angle APX1 is equal to angle BPY3, since they are vertically opposite angles of intersecting line segments AB and X1Y3. Since the other two corresponding angles are equal, angle AX1P is equal to angle BY3P. Thus, by the AAA similarity criterion, triangle APX1 is similar to triangle BPY3. Since triangles APX1 and BPY3 are similar, their sides will be in the same proportion. Thus, AP upon BP is equal to AX1 upon BY3. By construction, AX1 upon BY3 is equal to 1/3. Thus, AP upon PB is also equal to 1/3. In other words, the ratio AP is to PB is 1:3. Now, let us learn how to draw a triangle similar to a given triangle according to a given scale factor. But, what is the scale factor? You will find a scale factor on most maps. A unit of length on this map represents 500 units of actual length. You can also say that this map is 500% smaller than the actual place it shows. A scale factor determines how large or small an object is in comparison with another object. Construct a triangle similar to the triangle ABC with its sides 2 by 3 of the corresponding sides of the triangle ABC. Will the required triangle be smaller or larger than the given triangle? Since the sides of the new triangle will be 2/3 of the sides of the triangle ABC, it will obviously be smaller than the given triangle. Now, let us start with our construction. As step 1, draw a segment of a convenient length making an acute angle with the side of the given triangle. Here, let us draw the segment AX making an acute angle with the side AB of the triangle ABC. Now, you have to mark a few points at an equal distance from each other on AX. The number of points depends on the given scale factor. If the scale factor is x by y, the number of points is equal to the larger value amongst x and y. Here the given scale factor is 2 by 3. So the number of points you will mark on AX is 3, since between 2 and 3, 3 is greater. Now open the compass to a small convenient length. At step 2, mark 3 points x1, x2 and x3 on AX so that AX1 is equal to x1 x2 is equal to x2 x3. Make sure that the distance to which the compass is open is not disturbed as you mark the points. As step 3, draw a line to join the points x3 and B. Now, locate the smaller value in the given scale factor 2 by 3. It is 2. So at step 4, draw a line parallel to x3b from the point x2 to intersect AB at point P. Finally, as step 5, draw a line parallel to side BC at P to intersect side AC at Q. Triangle APQ is similar to the given triangle ABC, and its sides are 2 by 3 of the corresponding sides of the triangle ABC. Thus, APQ is the required triangle. Now, let us verify this construction mathematically. From the figure, we can see that AB is equal to AP plus PB. Dividing both sides with AP, we get an equation that we'll call equation 1. By construction, PB by AP is equal to 1 by 2. Putting this value in equation 1, we get AB by AP as 3 by 2 or AP by AB as 2 by 3. In triangles ABC and APQ, PQ is parallel to BC. Thus, triangle ABC is similar to triangle APQ using the AA similarity criterion. Since similar triangles have their corresponding sides in the same ratio, we see that our construction is verified mathematically. The triangle APQ is smaller than the given triangle ABC. Now, let us construct a triangle similar to and larger than triangle ABC. Construct a triangle similar to the triangle ABC with its sides 4 by 3 of the corresponding sides of the triangle ABC. As step 1, draw a segment of a convenient length making an acute angle with the side of the given triangle. Here, let us draw the segment AX making an acute angle with the side AB of the triangle ABC. Now, you will have to mark a few points at an equal distance from each other on AX. As before, the number of points is equal to the larger value amongst the given scale factor. Here the given scale factor is 4 by 3, so the number of points you will mark on AX is 4. Now open the compass to a small convenient length. As step 2, mark 4 points x1, x2, x3 and x4 on AX so that AX1 is equal to x1, x2 is equal to x2, x3 is equal to x3, x4. Make sure that the distance to which the compass is open is not disturbed as you mark the points. Now, locate the smaller value in the given scale factor 4 by 3. It is 3. So as step 3, draw a line to join the third point x3 to B. As step 4, draw a line parallel to x3b from point x4. As step 5, extend the side AB of the triangle ABC to meet the line drawn from the point x4 at P. As step 6, draw a line parallel to side BC at P as shown. Finally, as step 7, extend the side AC of the triangle ABC to meet the line drawn from point P at point Q. Triangle APQ is similar to the given triangle ABC, and its sides are 4 by 3 of the corresponding sides of the triangle ABC. Thus, APQ is the required triangle. Now, let us verify this construction mathematically. In triangles ABC and APQ, PQ is parallel to BC. Thus, triangle ABC is similar to triangle APQ. Since triangles ABC and APQ are similar, their corresponding sides will be in the same ratio. Since BX4 is parallel to BX3, triangles AX4P and AX3B are similar. Thus AP by AB is equal to AX4 by AX3. By construction, AX4 by AX3 is equal to 4 by 3. Thus AP by AB is equal to 4 by 3. Hence all sides of the triangle APQ are 4/3 of the corresponding sides of the triangle ABC. Now, let us learn how to draw tangents to a circle from an external point. Draw tangents to the circle with a center O from point P lying outside the circle. How many tangents can you draw to the circle from point P? Only 2. You can draw only 2 tangents to a circle from an external point. Let us start with the construction. As step 1, join the external point P with the center of the circle O. As step 2, we have to draw the perpendicular bisector of line segment OP. To draw the perpendicular bisector of OP, open the compass a little more than half of OP. Place the compass at O and mark 2 arcs above and below OP as shown. Next, place the compass at P and mark the 2 arcs above and below OP to intersect the arcs marked in the last step. Join the intersection points to get the perpendicular bisector of OP that intersects OP at M. Thus M is the midpoint of OP. As step 3, draw a circle with its center at M and radius equal to MO. This circle intersects the given circle at 2 points A and B. Finally, as step 4, join AP and BP. These are the 2 required tangents. Now, let us verify our construction mathematically. To verify this construction, let us draw a line to join the points O and A. Now, consider angle PAO. It is an angle in the semicircle and therefore equal to 90 degrees. So we can say that PA is perpendicular to the radius OA of the circle. By definition, PA is therefore a tangent to the given circle. Similarly, PB is also a tangent to the given circle. You've reached the end of this section. In this section, you learn to divide a given line segment into a given ratio, construct a triangle similar to a given triangle as per the given scale factor, construct a pair of tangents from a point external to a circle. Hope you enjoyed the learning experience. Welcome to the lesson on the areas of sector and segment of a circle. At the end of this lesson, you will be able to calculate the area of the sector of a circle, the length of an arc of a sector, and the area of the segment of a circle. Felix is aspiring to be a landscape designer like his father. His father had promised him that during summer break, he could assist him on some of his projects. So here he is, in his father's studio, learning the basics of landscaping design. The project he's working on requires redesigning Mrs. Carter's garden. Mrs. Carter wants her garden to look exactly like the one shown in the picture. It should be circular with a fountain in the middle. Mrs. Carter is a perfectionist, and she likes everything to be perfectly symmetrical. So, Felix's first task is to draw an accurate plan on paper. On analyzing the picture, he finds that the garden is made up of a number of sectors and segments. In order to draw an accurate design, he will need to apply his geometrical skills. Let's see how he manages this task. Felix first draws a circle with the center O. Next, he wants to divide the circle into 6 equal sectors. For this, he draws a chord that passes through the center. Recall that this chord is the diameter of the circle. Next, he draws 2 more diameters. He now has 6 equal sectors. The angles of each sector are 60 degrees. Recall that the part of a circle enclosed by 2 radii and the corresponding arc is called the sector of a circle, and the angle subtended by the corresponding arc of the sector at the center of the circle is called the angle of the sector. Next, Felix draws some more chords as shown. Each chord divides the sector into 2 parts, where one part is a triangle and the other is a segment. Now he has 6 segments. Recall that the part of a circle enclosed by a chord and the corresponding arc is called a segment of the circle. As per Mrs. Carter's requirement, the triangular parts must be covered with grass and the segments with yellow flowers. Felix shows the design to his father, who is very impressed by his neatness and precision. The next task given to Felix is to estimate the quantity of material that will be needed. For this, he will have to calculate the areas of the triangular parts and the segments. Let's see how he does this task. To calculate the area of the segment and the triangular portion, Felix must first calculate the area of the sector. Felix considers one of the sectors which he marks as OAPB. Here OA and OB are the 2 radii. He labels these as R. APB is the arc that subtends the angle AOB, which he marks as theta. The area of a circle is equal to pi multiplied by the square of the radius, that is, pi r square. Let's consider the circular region to be a sector forming an angle of 360 degrees at the center O. The area of this sector is equal to the area of the circle. This means that the area of a sector of angle 360 degrees is pi times radius square. By this relation, what will be the area of a sector with angle 1 degree? It would be equal to 1 divided by 360 multiplied by pi r square. Similarly, when the angle of the sector is theta degrees, the area of the sector will be equal to theta divided by 360 multiplied by pi r square. This is the formula for the area of a sector, where theta is the angle of the sector and r is the radius of the circle. Now, in the case of the garden, the angle theta is equal to 60 degrees and the radius is equal to 7 feet. Felix substitutes these values in the formula. The area of the sector OAPB is equal to 60 divided by 360 multiplied by pi times 7 square. The value of pi is taken as 22 upon 7. On simplifying these steps, the area of the sector OAPB is equal to 25.67 square feet. There may be situations when the lengths of the arcs of the sectors may also be required. So, how would this be calculated? Remember how the area of a sector was derived from the area of a circle? Using the same logic, the formula for calculating the length of the arcs can be derived. If the angle subtended by the arc is 360 degrees, then the length of the arc of a circle will be equal to the circumference of the circle. Thus, the length of an arc of angle 360 degrees will be equal to 2 pi r, where r is the radius of the circle. Similarly, the length of an arc of an angle 1 degree will be equal to 1 divided by 360 multiplied by 2 pi r. To generalize, if theta is the angle subtended by the arc at the center, then the length of the arc is equal to theta divided by 360 multiplied by 2 pi r. In case of the garden, the angle subtended by the arc is 60 degrees and the radius of the circle is 7 feet. On substituting these values in the formula for the length of an arc, the length of the arc AB is approximately equal to 7.33 feet. Now comes the next part, calculating the area of the segment of a circle. Let's see how Felix calculates this. The area of the segment APB is equal to the area of the sector OAPB minus the area of the triangle OAB. The area of the sector is equal to theta divided by 360 multiplied by pi r square. Recall that the area of a triangle can be calculated as half the product of the base and its corresponding height. Now, the question is, how do you calculate the base and the corresponding height of the triangle? The base and height can be calculated with the help of trigonometric ratios. In triangle AOB, angle AOB is 60 degrees and the side that is equal to the radius of the circle is 7 feet. Now, if a perpendicular is drawn on AB, it will bisect side AB as well as the angle AOB. Recall the theorem. A perpendicular drawn to a chord of a circle from its center divides the chord and the angle subtended by the chord into two equal parts. Thus AM is equal to BM and angle AOM is equal to angle BOM. So angles AOM and BOM are equal to 30 degrees. Now from triangle OMA, OM divided by OA is equal to cos 30 degrees. This implies that OM divided by 7 is equal to the square root of 3 divided by 2. On simplification, we get OM equal to 7 multiplied by the square root of 3 divided by 2. Similarly, AM divided by OA is equal to sine 30 degrees. This implies that AM divided by 7 is equal to 1 upon 2. On simplification, AM is equal to 7 divided by 2. Now base AB is equal to twice AM. This implies that AB is equal to 7 feet. Now the area of triangle OAB is equal to the half of the product of AB and OM. Substitute the values of AB and OM. Let's use the values of the square root of 3 is equal to 1.73. The area of the triangle is nearly equal to 21.19 square feet. Let's substitute the areas of sector OAPB and triangle OAB in equation 1. Therefore, the area of the segment is equal to 4.48 square feet. You have reached the end of the section. Before moving on to the next section, let's recap the key points covered. The arc of a circle is a part of the circumference of the circle. The circular region enclosed by two radii and the corresponding arc of a circle is called the sector of a circle. The circular region enclosed between a chord and the corresponding arc is called the segment of a circle. The angle of a sector is the angle subtended by the arc of the sector. The circumference of a circle is equal to 2 pi r, where r is the radius of the circle. The area of a circle is equal to pi r square. The length of the arc of a sector of angle theta is theta divided by 360 multiplied by 2 pi r. The area of a sector of angle theta is theta divided by 360 multiplied by pi r square. The area of a segment is the area of the corresponding sector minus the area of the corresponding triangle. Hope you enjoyed this learning experience. Welcome to the lesson on areas of combination of plane figures. At the end of the lesson, you will be able to determine the area of combination of plane figures. Sam's father Joe is a carpenter. In his free time, Sam helps his father with his carpentry. Joe makes wooden furniture. He uses veneer of different colors to design the surface. Last Sunday, Joe helped his father to make a table. Its top had a design that looked like a circle inscribed in a square. As you can see, the circular region is in blue, and the rest of it is in white. Joe now wants to make a table with a different design, and he would like Sam to help him. He shows him the design he has created and asks Sam to cut the blue veneer. Here, Sam can see that the blue portion of the design is not a standard shape and wonders how he will be able to cut such a shape. Joe gives Sam two separate pieces of veneer, one square and one circular. Sam thinks for a while. Then he gets an idea. He places the circular veneer in the center of the square and draws an outline of the circle. Then he places the circular veneer on one corner of the square veneer and draws an outline of the quadrant of the circle. Similarly, he marks quadrants on the rest of the corners. Finally, he cuts the marked portions of the blue veneer. Voila! There it is! He found a technique to remove the unwanted areas from the veneer to get the required design. Here's a recap of what Sam did. He took a blue square veneer, marked a circular shape in the center, and 4 quadrants on the corners. Then he cut the marked portions. If Sam wants to find the area of this shape, he simply has to subtract the area of the cut portions from the total area. In this case, the cut portions are a circle and 4 quadrants of a circle. That is, the area of the square minus the area of the circle minus the area of the 4 quadrants. Now, we will see how Sam and his father plan to make a door for the restaurant. The design of the door looks like this. It is 2 meters in height, 2 meters in width, consists of 2 wings, and the outer shape resembles a square. They would like to use glass and wood to make this door, where the glass occupies the semicircular shape on each wing of the door. Again, the combination of standard shapes, square and circle, is involved in the design of the door. Here they will have to cut 2 semicircles from the square that has a side of 2 meters. Now, they want to order the glass for the door. For this, they have to calculate the area of the glass required. You can observe that the glass portions of the door are semicircular in shape. Therefore, the area of the semicircle is the area of the glass. The diameter of the semicircle is the height of the door, which is equal to 2 meters. This implies that the radius is 1 meter. Recall that the area of the semicircle is half pi r square. Therefore, the area is equal to 1.57 square meters. Therefore, the area of the glass required to make the door is 2 times 1.57 square meters, that is 3.14 square meters. Then, what is the required area of the wood? The wood required is equal to the total area of the door minus the area of the glass. The door resembles a square, where each side equals 2 meters. Therefore, the total area of the door is 4 square meters. So the area of the wood required is the area of the door minus the area of the glass, which is equal to 0.86 square meters. This means that Joe needs to buy nearly 1 square meter of wood. This is the advantage of designing on paper before building anything. So far, we have seen how Joe and Sam worked on furniture. Now, we will see a few more examples of how the areas of non-standard figures are calculated. The examples we will see here involve basic geometric figures such as circles, squares, triangles, rectangles, etc. Look at the first example. Here we have to calculate the area of the figure which has a non-standard form. Let's try to analyze the figure. We can visualize the figure as 3 parts. It is a combination of a rectangle and 2 semicircles. Therefore, the area of the figure is the sum of the areas of a rectangle and the 2 semicircles. Let's see another example to understand the method better. Here's a figure composed of 2 concentric circles. To obtain the area of the shaded region, let's follow the procedure. Now, the area of the shade region is equal to Here's another example. This figure is a combination of a circle and a square. Here we have to find the area of the shaded region. Let's analyze the figure. You have reached the end of this section. Before moving on to the next section, let's recap the key points covered. In this lesson, we have tried to understand that a non-standard shape is composed of different standard shapes. We have also seen how to calculate the area of the non-standard shapes. Hope you enjoyed this learning experience. Welcome to the lesson on surface areas and volumes of combinations of solids. At the end of this lesson, you will be able to calculate the surface area and volume of a cube, cuboid, sphere, hemisphere, cylinder and a cone. Additionally, you will be able to calculate the total surface area and volume of a solid composed of a combination of fundamental solid shapes. The solid shapes that we have encountered so far in mathematics are simple fundamental shapes like cubes, cuboids, spheres, cylinders or cones. You have also learned how to solve problems that are related to surface areas and volumes of these shapes using standard formulae. Let us revisit the standard formulae for calculating areas and volumes of fundamental solid shapes. The curved surface area, or CSA, is the area of the curved surfaces for the solid. The remaining surfaces of the solid are the flat or the non-curved surfaces. In a cone, the flat surface is the circular area of the base. In a cylinder, the flat surfaces are the top and bottom circular areas. A sphere has no flat surface, whereas a cuboid and a cube have only flat surfaces. The flat surface area and the CSA of a solid together add up to the total surface area, TSA, for the solid. Take a moment to review all the formulae. You must remember the formulae in order to solve problems on areas and volumes of solids. In real life, you will encounter a variety of complex shapes which are made up of a combination of simple solids. When you try and solve problems on surface areas and volumes for complex shapes, you run up against difficulty. You cannot directly apply the standard formulae to these complex shapes. There is, of course, a fairly simple approach that is used for calculating areas and volumes. The trick lies in recognizing the fundamental solid shapes which make up the complex shape. A simple approach used for calculating the surface area and volume for complex shapes is: split up the complex solid shapes into fundamental solid shapes. Apply a standard formulae to the fundamental shapes to calculate areas or volumes and add the results of the calculation. This brings us to the end of this section. Hope you enjoyed your learning experience. Welcome to the lesson on the conversion of solids from one shape to another. At the end of this lesson, you will be able to set up an appropriate equation which will lead to a solution for problems on the conversion of solids. You will also apply your knowledge to solve selected problems. When we cut a watermelon into slices, we are converting a solid shape into other solid shapes. Regardless of the size and shape of the slices, there is one fact that holds true of the whole process. The volume of all the slices together exactly equals the volume of the original watermelon. When we convert a solid of a given shape to a solid of another shape, the surface area usually changes. However, the volume is preserved. This is the basic principle that is at the heart of any problem in the conversion of solids from one shape to another. The volume of material that we start with and the volume that we end with remain the same. In many cases, a single solid item is converted to a number of items, and we are asked to compute the number of such items that can be produced. In other cases, we are given the available number of items of a converted solid. We are asked to compute the height, radius, or some other dimension of the converted solid. Whenever a solid shape is converted to another shape, the volume of the object on the left always equals the total volume of the objects on the right. This equality can be expressed as the equation volume of one object equals n into volume of each shape of the second object. The quantity n is the number of objects on the right. In some problems that we will be asked to solve, we will be provided with the shape and dimensions of both objects. We will be asked to determine the value of n. For the example on the screen, we convert a cuboid of dimensions 6 into 2 into 2 centimeters to a number of cubes of side 2 centimeters. We are asked to find n, which is the number of cubes produced. We will equate the volumes to get 6 into 2 into 2 equals n into 2 cubed. We will then solve for n to get n equals 3. In some problems, n is provided, but the dimension of the object may not be. We have to determine the value of the missing dimension. For the example on the screen, we convert 8 into 2 into 2 centimeter cuboid to 4 equal cubes. We are asked to find L, which is the length of the side of the cubes produced. We will equate the volumes to get 8 into 2 into 2 equals 4 into L cubed. We will then solve for L to get L equals 2. Yet another type of problem that we may be asked to solve is if the shape of an object is changed. We have to determine the resulting surface area. For the example on the screen, we convert 3 equal cubes of side 2 centimeters to a 6 into 2 into 2 centimeter cuboid. We are asked to find the total surface area of the cuboid. When a solid changes shape, even though the volume remains the same, the change in geometry of the shape causes the surface area to change. We will use the standard formula to calculate the surface area for the resulting cuboid, which works out to 56 square centimeters. It is interesting to compare the areas for the initial and final shapes. The surface area for the 3 cubes is equal to 3 into 6 into L square, where L is the length of the side of a cube. This evaluates to 72 square centimeters. We have evaluated the surface area of the cuboid to be 56 square centimeters. As is evident, the areas are not equal. Welcome to the lesson on the frustum of a cone. At the end of this lesson, you will be able to define the frustum of a right circular cone. You will also be able to determine the surface area of the frustum of a cone. Additionally, you will be able to determine the volume of the frustum of a cone. Bucksack is an enthusiastic gardener. He has just bought additional flower pots for his garden and is planning to buy some paint for the new pots. He is also planning to buy some soil to fill the pots. As Bucksack leaves for his shopping, he realizes that he does not have the slightest idea how much paint he requires or how much soil he should buy. Actually, Bucksack needs to buy enough paint to cover up the curved surface area of all the flower pots. The amount of soil he needs to buy equals the volume of all the flower pots. The flower pots that Bucksack has bought have a shape called the frustum of a cone. A frustum of a cone is created by slicing off the top of a cone. As a definition, we may say that when we cut a right circular cone with a plane parallel to the base of the cone, then the solid shape between the plane and the base of the cone is called the frustum of a cone. The surface area and the volume of the frustum of a cone can be calculated using standard formulae. The CSA of the frustum of a cone equals pi into L into R1 plus R2, where R1 and R2 are the radii of the larger and smaller circular faces of the frustum respectively. L is the slant height of the frustum. The slant height can also be expressed as root h square plus R1 minus R2 the whole square, where R1 and R2 are the radii of the circular faces and h is the height of the frustum of the cone. Using the expression for L, the CSA of the frustum can also be expressed as pi times R1 plus R2 into under root h square plus R1 minus R2 the whole square. The formula for total surface area TSA for the frustum of a cone is pi times L times R1 plus R2 plus pi times R1 square plus pi R2 square. As before, the slant height L equals under root h square plus R1 minus R2 the whole square. The formula for volume of the frustum of a cone is 1 upon 3 times pi h times R1 square plus R2 square plus R1 R2, where R1 and R2 are the radii of the larger and the smaller circular faces of the frustum respectively, and h is the height of the frustum.
These two players have played 10 matches in all. Who's better? Here's the comparison of their performances.
Looking at the average, player 16 is definitely better.
Welcome to the lesson on the mean of grouped data. At the end of this lesson, you will be able to define the mean of grouped data. You will also be able to calculate the mean of grouped data using the direct method, the assumed mean method, and the step deviation method. Meet Miss Greenfingers. She is actively involved with the tree plantation programs in her city, but looks like something is troubling her. Here is the data for the tree plantation program that Miss Greenfingers recently conducted in 60 schools in her city. Now she has to find the average number of trees planted in each school. Let's help her to do it. First, let's observe the table carefully. What does it represent? The table shows the data for a tree plantation program as a grouped frequency distribution table. To find the average number of trees planted in each school, Miss Greenfingers has to find the mean of this grouped data. Recall that the mean of a given set of data is equal to the sum of the values of all the observations divided by the number of observations. There are three ways of calculating the mean: the direct method, the assumed mean method, and the step deviation method. Let us learn about these methods in detail. Let us begin with the direct method. What do the two columns in this table represent? The first column represents the class interval of group data, and the second column represents the frequency for each class interval. The first step to finding the mean of grouped data using the direct method is to find the class mark for each class interval. Let's denote the class mark as xi. The xi for each class is equal to half the sum of the upper and lower class limits of each class interval. Using the formula, we can calculate the class mark for each class interval. The class mark for the first class interval is equal to half the sum of 5 and 25. That is, half of 30, which is 15. Similarly, the class mark for the second class interval is 35. The remaining class marks are calculated and given in the table. Next, let us find the product of the frequency and the class mark for each class interval. This is denoted by Fi(xi). Now observe carefully how we calculate the value of Fi(xi). As you observed, for the first class interval, Fi(xi) is the product of 12 and 15, which is equal to 180. Similarly, for the second class interval, Fi(xi) is 280. The remaining products are shown in the table. Now, let us find the sum of the products of the frequencies and the class marks for all the class intervals. This sum is represented by summation Fi(xi), which is equal to 3300. We are close to finding the solution for Miss Greenfinger's problem. The mean x-bar of this grouped data is equal to the sum of the products of the frequencies and the class marks for all the class intervals divided by the sum of all the frequencies. On calculation, we get the mean of the given grouped data as 55. Thus, the average number of trees planted in each school is 55. We arrived at this result by calculating the mean of the given data using the direct method. This method involves a lot of multiplication and addition. This method can be tedious if the class intervals and frequencies are large. Let us see if there is a simpler way to find the mean of group data. let us go back to the data table. We'll take up from the step where we calculated the class marks for the class intervals in the given data. We'll try using a different method, the assumed mean method for finding the mean. This method can also be used when the size of the class is not the same. Observe the class marks for different class intervals. Let us assume any one of these class marks to be the mean of the given data. Let's choose 35 as the assumed mean denoted by A. Now, let us find the difference between the class mark for each class interval and our assumed mean. We'll term it as deviation and denote it as DI. The deviation for the first class interval is 15 minus 35, or minus 20. Similarly, for the second class interval, the deviation is 35 minus 35, or 0, and so on. Now, let us find the product of the frequency and the deviation for each class interval. This is denoted by FI/DI. For the first class interval, this product is 12 multiplied by minus 20, which is equal to minus 240. Similarly, for the second class interval, this product is 0. The product for the remaining class intervals are calculated and shown in the table. Next, we'll find the sum of the products of the frequencies and the deviations from assumed mean for all the class intervals. This sum is represented by the Greek symbol summation and read as summation. In this case, this sum represented by summation FI/DI is equal to 1200. Now, let us see how we can use this value to find the mean of the given grouped data. For this, we will have to derive a formula. Let's consider the summation FI/DI. Since DI is equal to xi minus a, we can substitute this in the above equation. Next, we'll divide both sides of the equation by summation Fi. The right side of the equation can be expressed as follows. Since summation Fi/xi divided by summation Fi is equal to the mean x bar, let's rearrange the equation. Here, x bar is the mean, a is the assumed mean, and summation Fi/DI divided by summation Fi is the mean of deviations. Thus, we arrive upon a formula where the mean of the given data is equal to the sum of the assumed mean and the mean of deviations. Now, let's use this formula to calculate the mean of the given grouped data. Substituting the values and calculating, we get the mean of the given grouped data as 55. This method is called the assumed mean method to find the mean of grouped data. Thus, we see that the mean found using the assumed mean method is in agreement with the value of the mean found using the direct method. Now, let us see if we can further simplify the calculations using another method to calculate the mean of grouped data. Let us go back to the step in the assumed mean method, where we chose one of the class intervals as the assumed mean and found the deviations for all other class intervals. We'll rework from here using a different approach. Observe the class intervals in this table carefully. Note that the class size for all the class intervals is 20. The class size is the difference between the upper class limit and the lower class limit. It is denoted by the letter H. Now, for each class interval, let us divide the deviation from assumed mean by the class size. This value is denoted by UI. The value of UI for the first class interval is equal to minus 20 divided by the class size 20, which is equal to minus 1. Similarly, for the second class interval, this value is 0. The remaining values are shown in the table. Now, let us find the product of ui and the frequency fi for each class interval. This is denoted by FIUI. For the first class interval, this product will be equal to 12 into minus 1, which is equal to minus 12. Similarly, for the second class interval, this value will be 0. The remaining values are provided in the table. Now, let us add the products of fi and ui for all the class intervals. This value summation FIUI in this case comes to 60. Now, let us see how we can use this value to find the mean of the given grouped data. This involves a bit of derivation. Let us start with the relation we found in the assumed mean method. Since ui is equal to di divided by h, we can say di is equal to the product of ui and the class interval h. Substituting this value in the equation, we find a relationship between the mean x bar, ui and h. Further substituting in the values, we find that the mean of the given grouped data is 55. This method is called the step deviation method. It is also used to find the mean of grouped data. Thus, we see that the mean found using the step deviation method is in agreement with the value of the mean found using the assumed mean and the direct method. Welcome to the lesson on the mode of grouped data. At the end of this lesson, you will be able to define the mode of grouped data. You will also be able to calculate mode of grouped data. Miss Greenfinger's heart beats for the trees. She recently conducted a tree plantation program in 60 schools of her city. Now, why is she looking so hassled? Actually, Miss Greenfingers is preparing a project report. She has to find the maximum number of trees planted across all 60 schools. Now, what does this mean? Look at this example. The data for 6 schools is given here. Which value representing the number of trees planted is repeated frequently? Note that 6 trees are planted in one school, 2 trees are planted in 2 schools, and 4 trees are planted in 3 schools. In this case, 4 is occurring the maximum number of times. Now, coming back to Miss Greenfinger's data, let's help her find the maximum number of trees planted across all 60 schools. She has the grouped data of all 60 schools that participated in the tree plantation program. Observe the data presented in the grouped frequency distribution table. To find the maximum number of trees planted across the 60 schools, Miss Greenfingers has to find the mode of this grouped data. Recall that the mode of a given set of data is the observation with the maximum frequency. Now, let us find the solution to Miss Greenfinger's problem. The table represents the class interval of the grouped data and the frequency for each class interval. The first step towards finding the mode of the grouped data is to locate the class interval with the maximum frequency. In the given data, the maximum frequency is 20. The class interval corresponding to the maximum frequency is called the modal class. Here the modal class is 65 to 85 as it corresponds to the maximum frequency of 20. The mode of this data is calculated using the formula shown here. Now, let us find what each term in this formula represents. In the formula for mode, L stands for the lower class limit of the modal class. In this case, the value of L is 65, which is the lower class limit of the modal class 65 to 85. The H stands for the class size. While finding the value of H, we assume that all class intervals have the same class size as in the case of this table. Here the value of H is 20. Next, in the formula, F1 stands for the frequency of the modal class. In this case, the modal class is 65 to 85 and its frequency F1 is 20. Moving on in the formula for mode, F0 stands for the frequency of the class preceding or just before the modal class. In this case, the class preceding the modal class is 45 to 65 and its frequency F0 is 14. Finally, in the formula for mode, F2 stands for the frequency of the class succeeding or just after the modal class. In this case, the class after the modal class is 85 to 105 and its frequency F2 is 6. Now, let's substitute the values of L, H, F1, F0 and F2 in the formula for calculating mode. Let's simplify this expression further. The mode of a given data is equal to 71. Miss Greenfinger's problem is solved. The mode or the same number of trees planted in maximum number of schools as per the given data is 71. You've reached the end of this section. Before moving on, let's review the key points covered in this section. The mode of a given set of data is the observation with the maximum frequency. The class interval corresponding to the maximum frequency is called the modal class. The formula to calculate the mode is as shown. Here, L stands for the lower class limit of the modal class. The H stands for the class size. F1 stands for the frequency of the modal class. F0 stands for the frequency of the class preceding or just before the modal class. F2 stands for the frequency of the class succeeding or just after the modal class. Welcome to the lesson on the median of grouped data. At the end of this lesson, you will be able to define the median of grouped data and explain the concept of cumulative frequency. You will also be able to calculate the median of grouped data. Ms. Greenfingers is actively involved with the tree plantation programs conducted in her city. Here is the data for the tree plantation program Ms. Greenfingers recently conducted in 60 schools. The data is shown as a grouped frequency distribution table. Ms. Greenfingers has to find the median of this group data. Recall that the median of a given set of data is the observation that lies in the middle of the data. Observe the grouped frequency table. What do the two columns in this table represent? The first column represents the class interval of the group data, and the second column represents the frequency for each class interval. Now, observe the class intervals in the first column. Each class interval has a lower class limit, highlighted in yellow, and an upper class limit, highlighted in blue. Next, we'll rewrite the number of trees planted using only the lower class limits of all the class intervals. We can write the first class interval, 5 to 25, as more than or equal to 5. Similarly, we can write the second class interval, 25 to 45, as more than or equal to 25, and so on. Now, observe the number of schools in the frequency column. Will the frequencies remain unchanged, or do these frequencies need to be adjusted as per the new class intervals? From the new class intervals, it is clear that all the schools have planted at least 5 or more than 5 trees. Thus, the adjusted frequency of the first class interval is the total number of schools, which is equal to 60. The adjusted frequency for the second class interval is not 8, but 48. Similarly, the adjusted frequencies for the remaining class intervals are calculated. This new adjusted frequency is called the cumulative frequency. Now, let us combine this table with the original table showing the actual class intervals. The table here now represents the cumulative frequency distribution of the more than type. There is one more type of cumulative frequency distribution. Let's see how it is calculated. Now, we'll rewrite the number of trees planted using only the upper class limit of all the class intervals. The first class interval, 5 to 25, can be written as less than 25. The second class interval, 25 to 45, can be written as less than 45. The other class intervals can also be rewritten similarly. Now, observe the number of schools in the frequency column. Here too, the frequencies will need to be adjusted as per the new class intervals. From the new class intervals, it is clear that 12 schools have planted less than 25 trees. Hence, the adjusted frequency for the first class interval remains 12. However, the number of schools that planted less than 45 trees is the sum of the frequencies of class intervals less than 45 and less than 25. That is, 12 plus 8, which is equal to 20. Thus, the adjusted frequency of the second class interval is 20. Similarly, the adjusted frequency for the third class interval is equal to 12 plus 8 plus 14, which is equal to 34. This adjusted frequency is also called the cumulative frequency. Now, let us combine this table with the original table showing the actual class intervals. The table here now represents the cumulative frequency distribution of the less than type. Preparing a cumulative frequency distribution table is the first step for calculating the median of the group data. You can use the cumulative frequency distribution of either the more than or the less than type to find the median of grouped data. Now, we'll use the cumulative frequency distribution of the less than type to find the median of the number of trees planted. The first step is to find half of the total number of observations. The total number of observations is given by the sum of all the frequencies and denoted by n. In this case, n is equal to 60. So, half of the total number of observations is equal to n by 2, which is equal to 30. Note that to calculate n, or n by 2, we use the frequency and not the cumulative frequency data. The next step is to locate the median class. The median class is the class interval with the cumulative frequency more than and closest to the value of n by 2. In this case, n by 2 is 30. The cumulative frequency of class interval 45 to 65 is 34, that is, more than and closest to 30. Thus, 45 to 65 is the median class for this data. The median of grouped data is calculated using the formula shown here. Let us see what each term in this formula stands for. The L in the formula for median stands for the lower class limit of the median class. In this case, L is equal to 45. The N in the formula for median stands for the total number of observations. In this case, N is equal to 60. The symbol CF in the formula of median stands for cumulative frequency of the class preceding the median class. In this case, the median class is 45 to 65 and the class preceding it is 25 to 45. This class has a cumulative frequency of 20. Thus, the value of CF in this case is 20. The symbol F in the formula of median stands for frequency of the median class. In this case, the median class is 45 to 65, and its frequency of value F is 14. The symbol H in the formula of median stands for the class size of class intervals in the given table, assuming all class sizes are equal. In this case, the class size H is 20. Putting in the values of different terms and calculating, we get the median of the given data as 59.28. We have found the answer to Miss Greenfinger's problem. Now she can say that around 50% of the schools planted less than 59 trees, while the other 50% of the schools planted more than 59 trees in her tree plantation program. You have reached the end of this section. Before moving on to the next section, let's recap the key points covered. The median of a given set of data is the observation that lies in the middle of the data. The cumulative frequency of a class is obtained by adding the frequencies of all the classes preceding the given class. There are two types of cumulative frequencies, the less than type and the more than type. Preparing a cumulative frequency distribution table is the first step in calculating the median of the group data. The cumulative frequency distribution of either the more than or the less than type can be used to find the median of group data. The formula for the median of grouped data is shown here. In this formula, L is the lower class limit of median class. N is the total number of observations. CF is the cumulative frequency of class preceding the median class. F is the frequency of median class. H is the class size of class intervals. Hope you enjoyed your learning experience. Welcome to the lesson on the graphical representation of cumulative frequency distribution. At the end of this lesson, you will be able to define an ogive, also called a cumulative frequency curve. You will also be able to draw ogives for the less than and the more than types of cumulative frequency distributions. Miss Greenfingers has recently completed a tree plantation program for the local schools in her city. In all, 60 schools participated in the program. She has the data of the number of trees planted during the program in a frequency distribution table. Here, the first column displays the class intervals and the second displays the frequency. Can we represent this data graphically? Yes, we can. Recall that you have learned to represent group data using bar graphs, histograms, or frequency polygons. Let's see another way of representing this data. First, class intervals are rewritten using lower class limits only. Next, their corresponding frequencies are adjusted as shown. Now, we have the cumulative frequency distribution of the more than type. Similarly, the cumulative frequency distribution of the less than type is prepared. For this, the data is first reorganized using only the upper class limits of the class intervals. Then, their corresponding frequencies are adjusted as shown. The cumulative frequency distribution of the less than type is obtained. Next, we'll see how this reorganized data is represented in a graphical form. Let's first consider the cumulative frequency distribution of the more than type. This data, if represented graphically, results in a curve, which is called an ogive or a cumulative frequency curve. An ogive is defined as a curve that represents the cumulative frequency distribution of grouped data. To draw an ogive for this data, we will need a Cartesian plane. Here, we'll plot the lower class limits of the data on the x-axis and their corresponding cumulative frequencies on the y-axis. Let's choose any comfortable scale to mark the lower class limits on the x-axis. We'll take a scale of 1 centimeter equal to 10 units, which is equal to 10 trees on the x-axis. Then, we'll label these with the lower class limits of the class intervals. Next, we'll choose a suitable scale to mark the reference points for the cumulative frequency on the y-axis. We'll take a scale of 1 centimeter is equal to 5 units, which is equal to 5 schools on the y-axis. We can label the x-axis as lower limits of data, or simply as lower limits, and the y-axis as cumulative frequency. Next, we'll mark points on the graph that represent the cumulative frequency corresponding to the lower limits of the class intervals. For example, for the lower limit of 5, the cumulative frequency is 60. Similarly, we'll mark the points corresponding to cumulative frequencies of the other lower limits of data. Finally, we'll draw a smooth curve to join all the points marked on the graph. This curve is a cumulative frequency curve, or ogive. Since in this case, the ogive represents a cumulative frequency distribution of the more than type, it is called a more than ogive. Now, let's draw an ogive representing the cumulative frequency distribution of the less than type. The table here shows the cumulative frequency distribution of the less than type. Let's start plotting the ogive for this data. Here's the Cartesian plane. To draw a less than type ogive, we'll plot the upper class limits of the data on the x-axis and their corresponding cumulative frequencies on the y-axis. We'll label the x-axis as upper limits of data or simply as upper limits. Next, label the y-axis as cumulative frequency. Next, we'll choose a scale to mark the upper class limits on the x-axis. Here, we'll take a scale of 1 centimeter equal to 10 units, which is equal to 10 trees planted. Next, we'll choose a suitable scale to mark reference points for cumulative frequency on the y-axis. Here we'll take a scale of 1 centimeter equal to 5 units, which is equal to 5 schools. Next, we'll mark a point above each upper limit of data on the x-axis corresponding to its cumulative frequency on the y-axis. For example, for the upper limit of 25, the cumulative frequency is 12. Similarly, we'll mark the points corresponding to cumulative frequencies of other upper limits of data. Finally, draw a smooth curve to join all the points marked on the graph. Here's the required ogive. It is an ogive of the less than type. Ogives can also be used to find the median of grouped data. Let's see how this is done. From this table, we can see that the total number of observations of the value of n for this data is 60. So n by 2 is equal to 30. Now, let's locate the value of n by 2 on the y-axis. We'll draw a line parallel to the x-axis from the point denoting n by 2 to intersect the ogive. From this point of the ogive, draw a line perpendicular to the x-axis. The point where the perpendicular intersects the x-axis gives the median of the grouped data. As you can see, you can use either the more than or the less than ogive to find the median of the grouped data. In both cases, the median of the given grouped data is approximately 59. There is another way of finding the median of the grouped data using the ogives. We can draw both the less than and the more than ogives on the same chart. The two ogives will intersect at a point. Draw a perpendicular to the x-axis from the point at which the two ogives intersect. The point where the perpendicular intersects the x-axis gives the median of the grouped data. Note that, by this method, the median of this grouped data is also approximately 59. You have reached the end of this section. Before moving on to the next section, let's recap the key points covered. An ogive, or cumulative frequency curve, is a curve that represents the cumulative frequency distribution of grouped data. An ogive representing a cumulative frequency distribution of the more than type is called a more than ogive. An ogive representing a cumulative frequency distribution of the less than type is called a less than ogive. Ogives can be used to find the median of grouped data. The median of grouped data can be obtained graphically by plotting the ogives of the less than type and the more than type. The x-coordinate of the point of intersection of the two ogives is the median of the grouped data. Hope you enjoyed your learning experience. Welcome to the lesson on probability, a theoretical approach. At the end of this lesson, you will be able to distinguish between experimental and theoretical probability. You will also be able to calculate the theoretical probability of an event. Meet Mr. Gamerman, the biggest fan of board games in the whole world. From Ludo to Monopoly, he loves them all. There is one thing Mr. Gamerman hates about all board games. That is, trying to get a 6 on the first roll of a die. He always seems to roll a number other than 6, but he always wants to get a 6 on the first roll. What are the chances or probability of him rolling a 6? Mr. Gamerman is determined to find the answer. He performs an experiment in which he rolls the die and records the number he gets each time. To get reliable results from his experiment, Mr. Gamerman rolls the die dozens of times. No, make that hundreds of times. Actually, make that a few thousand times. As per Mr. Gamerman's experiment, the total number of throws of the die is 4,000 and the number of sixes rolled is 640. Divide the number of sixes rolled by the total number of throws. That is 640 divided by 4,000. The result obtained is 0.16, which is equal to approximately 1 upon 6. This is the probability of getting a 6 on the roll of a die. Since the probability is based on the observations of an experiment, it is called an experimental or empirical probability. Like Mr. Gamerman, many people across the globe have performed such experiments in the past. The experimental probability in most cases settles around 1 upon 6. Or 0.16. Now, let's analyze the activity of rolling a die. A die when rolled will always show a number from 1 to 6. Here, we'll assume that the die is fair or unbiased. This means that if Mr. Gamerman rolls the die, then all the numbers from 1 to 6 have an equal probability of showing up. The possible outcomes when the die is rolled are 1, 2, 3, 4, 5 and 6. These outcomes are said to be equally likely. Thus, the total number of possible outcomes is 6. Out of the total number of possible outcomes, how many are favorable? By favorable, we mean how many possibilities allow Mr. Gamerman to get a 6. Clearly, there is only one such possibility when the die rolls a 6. Thus, there is only one favorable outcome. Therefore, the probability of getting a 6 on the roll of a die is the number of favorable outcomes divided by the total number of possible outcomes. In this case, it is equal to 1 upon 6, which is equal to approximately 0.16. This is called theoretical or classical probability. So now Mr. Gamerman's mind seems to be at rest. He now knows his chances of getting a 6. Please note that as the number of observations in an experiment increases, the experimental probability gets closer to the theoretical probability. Let's move on to learn more about calculating theoretical probability. The theoretical probability of an event E, denoted by P of E, is given by the number of outcomes favorable to E divided by the total number of possible outcomes. Now, observe the total number of possible outcomes when you roll a die. Each of these outcomes is called an elementary event. Now, let us investigate the probabilities of all the elementary events of rolling a die. The probability of getting the number 2 on the roll of a die is 1 by 6. The probability of getting the number 5 on the roll of a die is again 1 by 6. Similarly, we can show that the probability of getting any number 1, 2, 3, 4, 5 or 6 on the roll of a die is 1 by 6. What does this indicate? This indicates that the sum of the probabilities of elementary events of an experiment is 1. Now, let us get back to the probability of getting the number 1 on the roll of a die. As you already know, the probability of getting the number 1 on the roll of a die is 1 by 6. Now, let's consider another event. What is the probability of getting a number other than 1 on the roll of a die? The total number of possible outcomes when we roll a die is 6. In this case, the number of favorable outcomes is 5. Thus, the probability of getting a number other than 1 on the roll of a die is 5 by 6. Let us represent this event as 1 bar. Now, let us compare the probabilities of the last two events. Note that you cannot get 1 and a number other than 1 at the same time when you roll a die. The two events 1 and 1 bar shown here are mutually exclusive. That is, the events can only happen in the absence of each other. Such events are called complementary events. The sum of the probabilities of two complementary events is always equal to 1. Now, let us find the probability of getting the number 10 on the roll of a die. As you know by now, the total number of possible outcomes when you roll a die is 6. How many favorable outcomes are there on getting the number 10? Clearly, it is 0, since a die only has the numbers 1 to 6. So, the probability of getting a 10 on the roll of a die is 0. An event having 0 probability of occurrence is called an impossible event. Next, let's find the probability of getting a number less than 10 on the roll of a die. As you know by now, the total number of possible outcomes when we roll a die is 6. A die can show any number from 1 to 6 and all of them are less than 10. Thus, there are 6 favorable outcomes to rolling a number less than 10. The probability of getting a number less than 10 on the roll of a die is 1. An event having a probability of 1 is called a sure or certain event. You have reached the end of this section. Before moving on to the next section, let's recap the key points covered. The theoretical or classical probability of an event E, denoted by P of E, where P of E is equal to the number of outcomes favorable to E divided by the total number of possible outcomes. Here, it is assumed that the outcomes of the experiment are equally likely. The probability of a sure event or certain event is 1. The probability of an impossible event is 0. The probability of an event E is a number P of E such that 0 is less than or equal to P of E, which is less than or equal to 1. An event with only one outcome is called an elementary event. The sum of the probabilities of the elementary events of an experiment is 1. For any event E, P of E plus P of E bar is equal to 1, where E bar stands for not E. E and E bar are called complementary events. Experimental probability gets closer to the theoretical probability as the number of observations increase. Hope you enjoyed this session.